Right now, as you watch this, astronomers around the world are staring at their computer screens in disbelief. Something impossible just happened. The Event Horizon Telescope, the array of observatories that gave humanity its first photograph of a black hole, captured new images that defy explanation. The magnetic field surrounding the supermassive black hole at the heart of galaxy M87 has completely flipped. Scientists thought this would take millions of years, if it could happen at all. It happened in the span of a few years. The rules we thought governed these cosmic monsters might be wrong. Before we dive into what this means, picture yourself standing at the edge of reality itself, not metaphorically, literally. A black hole represents the boundary where the known laws of physics begin to crumble. Beyond that edge, time stops making sense. Space twists into impossible shapes. Light itself gets trapped, unable to escape. For decades, black holes existed only in mathematics, abstract solutions to Einstein's equations that seemed too extreme to be real. Then we found them, hundreds of them, thousands, lurking in the centers of galaxies, born from the deaths of massive stars, colliding and merging across the cosmos in displays of raw power that dwarf anything else in nature. You might think you understand black holes from science fiction or popular articles. The truth is stranger and more fascinating than any fiction. When Carl Schwarzschild first derived the mathematics of black holes in 1916, he was solving Einstein's field equations while serving on the Russian front during World War I. Within months of Einstein publishing General Relativity, Schwarzschild found a solution describing what would happen if you compressed enough mass into a small enough volume. The result shocked everyone, including Einstein himself, a point in space where gravity becomes so intense that the escape velocity exceeds the speed of light. Since nothing travels faster than light, nothing escapes. Not matter, not energy, not information. The name black hole didn't come until much later. For decades, physicists called them frozen stars, or collapsed objects, or simply avoided talking about them. The term black hole was coined in the late 1960s, and it stuck because it captures something essential about these objects. They are holes in the fabric of space-time, cosmic voids that devour everything around them. But calling them holes misses something crucial about what they actually do to reality. Imagine space-time as a stretched rubber sheet. Place a bowling ball on it, and the sheet dips down, creating a well. That's how massive objects curve spacetime, according to Einstein. Now imagine replacing that bowling ball with something infinitely dense, something that punches through the sheet entirely. That's closer to what a black hole does. It doesn't just curve spacetime, it tears it, creating a one-way membrane called the event horizon. Cross that boundary and you're gone. Not destroyed immediately, but removed from the universe we inhabit. Everything that falls past the event horizon continues falling toward the singularity at the center, a point of infinite density where all the mass gets compressed to zero volume. Here's where it gets strange. Time itself behaves differently near a black hole. If you watch someone fall toward the event horizon from a safe distance, you would never actually see them cross it. As they got closer, time would slow down for them relative to you. Their movements would appear to freeze, their light would redshift toward invisibility, and they would seem to hang suspended at the edge forever. But from their perspective, they would cross the horizon in finite time, experiencing nothing unusual at that moment. The falling would continue. Only later, as tidal forces grew stronger, would they realize the mistake. By then, escape would be impossible. Scientists classify black holes into three main types based on mass. Stellar mass black holes form when massive stars exhaust their nuclear fuel and collapse. These range from about 5 times the Sun's mass up to perhaps 100 solar masses. They're relatively common, with millions scattered throughout our galaxy alone. Then there are intermediate mass black holes, weighing between hundreds and thousands of solar masses. These are rare and poorly understood. We're not sure how they form or how many exist. Finally, at the extreme end, we have supermassive black holes. These cosmic behemoths weigh millions or billions of times more than the Sun and lurk at the centers of most large galaxies, including our own Milky Way. The existence of supermassive black holes raises fascinating questions. How did they grow so large? Did they form from the collapse of massive gas clouds in the early universe, or did they start small and grow through billions of years of feeding? Recent observations suggest both processes might contribute. Some supermassive black holes existed when the universe was less than 1 billion years old, which means they had to grow incredibly fast. Others seem to have grown more gradually, accreting matter from their surroundings and occasionally merging with other black holes when galaxies collide. But here's what makes black holes truly bizarre. Despite their reputation as cosmic vacuum cleaners, they don't actually suck matter in like a drain. Material doesn't fall straight down into a black hole. Because of angular momentum, basically everything in space is rotating or orbiting something else. Matter spirals inward, forming what we call an accretion disk. Picture water swirling down a drain, but on a cosmic scale, and superheated to millions of degrees. As gas and dust circle closer to the event horizon, friction heats the material until it glows brilliantly in X-rays and other high-energy radiation. The brightest objects in the universe aren't stars, they're the accretion disks around supermassive black holes, outshining entire galaxies. This brings us to M87, a giant elliptical galaxy sitting about 55 million light-years away in the constellation Virgo. It's one of the most massive galaxies in the nearby universe, containing trillions of stars and extending across 120,000 light-years. At its heart lies M87 star, a supermassive black hole weighing 6.5 billion times more than our Sun. To put that in perspective, if our Sun were the size of a ping-pong ball, M87 star would be larger than the entire solar system. Its event horizon measures about 24 billion kilometers across, roughly 4 times the distance from the Sun to Neptune. For decades, we knew M87 star existed because of its effects on surrounding matter. Astronomers could measure how fast stars and gas orbited the galaxy's center, calculating the mass of the invisible object holding everything in its gravitational grip. They observed a spectacular jet of plasma shooting out from the galactic core, extending 5,000 light-years into space and glowing across the electromagnetic spectrum. This jet, powered by the black hole's rotation and magnetic fields, contains particles accelerated to nearly the speed of light. But we couldn't actually see the black hole itself. That required something extraordinary. In the spring of 2019, scientists made an announcement that reverberated through the scientific community and captured public imagination worldwide. For the first time in human history, we had a photograph of a black hole, not an artist's interpretation, not a simulation, but an actual image constructed from observations of M87 star itself. The image showed exactly what Einstein's equations predicted: a dark circular shadow surrounded by a bright ring of glowing plasma. The shadow represents the event horizon plus the photon sphere, a region where light orbits the black hole before either escaping or falling in. The bright ring is emission from the accretion disk, bent around the black hole by gravitational lensing. Creating that image required turning the entire Earth into a telescope. The Event Horizon Telescope isn't a single instrument, but a network of radio observatories scattered across the globe, from Hawaii to Antarctica, from Chile to Spain. These telescopes observed M87 star simultaneously over several nights, recording petabytes of data that had to be physically shipped to processing centers because the volume was too large to transmit over the internet. Scientists then used a technique called very long baseline interferometry to combine the observations, effectively creating a telescope with an aperture the size of Earth. The resolution achieved was sharp enough to read a newspaper in New York from a cafe in Paris. That first image represented years of work by hundreds of scientists and engineers. It confirmed predictions made a century earlier and opened a new era of black hole astronomy. But it was just the beginning. The Event Horizon Telescope continued observing M87 star and other targets, gathering more data and improving techniques. Recently, they released new observations that have left astronomers scrambling to explain what they're seeing. The magnetic field around M87 star has changed, not just shifted slightly, it has completely reorganized itself. Polarization measurements, which reveal the orientation of magnetic field lines threading through the plasma, show a structure that's almost reversed compared to earlier observations. This shouldn't be possible, at least not on timescales of a few years. Magnetic fields in accretion disks are thought to be relatively stable, anchored by the rotation of the disk itself and the black hole's spin. Major reorganizations should take thousands or millions of years. Yet here we are, watching it happen in what amounts to the blink of an eye on cosmic timescales. Why does this matter? Because magnetic fields are crucial to understanding how black holes feed and how they launch those powerful jets. The leading theory, called the Blandford-Znajek mechanism, proposes that magnetic field lines threading the event horizon can extract rotational energy from the black hole itself, channeling it into the jets we observe. If magnetic fields can reorganize this quickly, it suggests the process is far more dynamic than we thought. It might mean that black holes can switch between different states, periods of intense activity followed by relative quiet, on timescales short enough for humans to observe. But wait, because in just a few minutes, I'm going to reveal how this discovery connects to dark matter, the invisible substance that makes up most of the mass in the universe. Scientists recently found a way to use black holes as detectors for dark matter, and the technique relies on precisely these kinds of magnetic field measurements. Stay with me. The changing magnetic field raises another question. What causes these reorganizations? One possibility involves instabilities in the accretion disk itself. As matter spirals inward, it can develop turbulent eddies and magnetic dynamos that amplify and twist field lines. Another possibility is that we're seeing the aftermath of a major feeding event. Perhaps M87 star recently consumed a large quantity of gas or even a smaller black hole, disrupting the accretion disk and causing the magnetic field to reconfigure. A third possibility, and this is where things get really interesting, is that we're observing magnetic reconnection events, sudden releases of stored magnetic energy that can heat plasma to billions of degrees and accelerate particles to relativistic speeds. Magnetic reconnection happens on the Sun all the time, causing solar flares and coronal mass ejections. But near a black hole, the energy scales are incomparably larger. A single reconnection event in M87 star's accretion disk could release more energy than our Sun will emit in its entire 10 billion-year lifetime. These events might be responsible for the variability we observe in black hole jets and could explain how particles get accelerated to such extreme velocities. To understand what's happening, we need to think about the anatomy of a black hole in more detail. The event horizon is just one feature. Surrounding it is a region called the ergosphere, which exists only for rotating black holes. Within the ergosphere, space-time itself is dragged along by the black hole's rotation. It's impossible to remain stationary there. Everything must rotate in the same direction as the black hole. This effect, called frame dragging, allows for the extraction of rotational energy through the Penrose process or the Blandford-Znajek mechanism I mentioned earlier. Just outside the event horizon lies the innermost stable circular orbit, the last point where matter can orbit without inevitably spiraling in. For a non-rotating black hole, this orbit sits at 3 times the Schwarzschild radius. For a maximally rotating black hole, it's much closer, allowing accretion disks to extend almost to the event horizon itself. This proximity means the inner regions of the disk orbit at significant fractions of light speed, and relativistic effects become important. Time dilation, length contraction, and extreme gravitational lensing all come into play, affecting what we observe. The plasma in the accretion disk isn't uniform. It's threaded with magnetic fields that exert forces on the charged particles, creating structure and driving turbulence. The magnetorotational instability, discovered in the 1990s, explains how initially weak magnetic fields can amplify through the differential rotation of the disk. Faster-moving inner regions drag field lines ahead of slower outer regions, twisting and strengthening them until the magnetic pressure becomes dynamically important. This process generates the turbulence that allows angular momentum to be transported outward, enabling matter to spiral inward. Scientists simulate these processes using supercomputers running general relativistic magnetohydrodynamics codes. These simulations solve Einstein's equations for space-time curvature, while simultaneously tracking the motion of plasma and magnetic fields. The calculations are so complex that even the world's fastest supercomputers can only simulate small regions for short times. Despite these limitations, simulations have successfully reproduced many observed features of black hole systems, including jet formation, disk variability, and quasi-periodic oscillations in X-ray emission. Yet the recent observations from the Event Horizon Telescope reveal behavior that current simulations struggle to explain. The rapid magnetic field reorganization we're seeing might indicate that our models are missing something fundamental. Perhaps the turbulence in the disk is more vigorous than we thought, or maybe magnetic reconnection plays a bigger role than current theories account for. Some researchers have proposed that general relativistic effects near the event horizon create conditions that amplify magnetic field changes, making the system far more dynamic than classical calculations would suggest. Understanding how black holes feed requires us to think about angular momentum. When gas falls toward a black hole, it rarely drops straight in. Most material in space has some rotation, some sideways motion relative to the black hole. Conservation of angular momentum means that as this material gets closer, it must spin faster. Just like an ice skater pulling in their arms speeds up their rotation. The result is an accretion disk, a swirling vortex of superheated plasma spiraling inward toward its doom. These accretion disks are some of the most extreme environments in the universe. The inner regions, close to the event horizon, orbit at significant fractions of light speed. At those velocities, relativistic effects dominate everything. Time runs slower, distances contract in the direction of motion, and the immense gravitational field bends light paths into curves and loops. Material in the inner disk can orbit the black hole several times before the light it emits finally escapes outward, creating complex patterns of emission that astronomers must carefully untangle to understand what's actually happening. The temperatures in accretion disks defy imagination. Friction between different layers of the disk, each orbiting at slightly different speeds, converts gravitational potential energy into heat. Near the event horizon of a supermassive black hole, temperatures can reach tens of millions of degrees. For stellar mass black holes, which are smaller and have steeper gravitational gradients, the inner disk can heat to billions of degrees. At these temperatures, matter exists as plasma, a soup of naked atomic nuclei and free electrons. The plasma radiates across the electromagnetic spectrum, from radio waves through visible light to X-rays and gamma rays. But temperature and radiation alone don't explain the full story of accretion. Magnetic fields thread through the plasma, connecting different regions of the disk and creating structure where simple gas dynamics would predict uniform flow. The magnetorotational instability I mentioned earlier generates turbulence that's essential for accretion to proceed. Without this turbulence, angular momentum couldn't be transported outward efficiently, and material would simply orbit the black hole forever, rather than falling in. Here's where the physics gets truly fascinating. The magnetic fields in the accretion disk aren't just passive structures carried along by the plasma. They actively shape the flow of matter and energy. Field lines act like elastic bands, storing energy when they're stretched or twisted. When the stress becomes too great, the field lines can suddenly reconnect, releasing stored energy in explosive bursts. These magnetic reconnection events might explain the rapid flares and variability we observe in many black hole systems. Recent observations suggest that magnetic fields also play a crucial role in launching jets. Nearly every actively feeding black hole produces jets to some degree, narrow beams of plasma and radiation shooting outward from the poles at velocities approaching light speed. In the case of M87, the jet extends over 5,000 light-years from the black hole, maintaining its narrow structure across distances that dwarf most galaxies. The energy required to power such a jet is staggering, equivalent to converting the mass of multiple stars into pure energy every year. The leading explanation for jet formation involves magnetic fields anchored in the accretion disk or threading through the black hole's event horizon itself. As the disk rotates, it winds up these field lines like twisting a rope. Eventually, the twisted field lines create a magnetic tower, a helical structure that channels plasma outward along the rotation axis. The Blandford-Znajek mechanism takes this further, extracting rotational energy directly from the spinning black hole through magnetic field lines that thread the ergosphere. This process can tap into the enormous reservoir of energy stored in the black hole's rotation, converting it into the kinetic energy of the jet. What makes the recent observations of M87 so significant is that they reveal this process in action, and it's behaving in ways we didn't predict. The magnetic field flip between observations suggests that the accretion flow isn't stable. Perhaps the disk goes through cycles of building up and releasing magnetic energy. Perhaps we're seeing the aftermath of a major disruption, like the black hole recently consuming a star or merging with a smaller black hole. The truth is, we don't yet know, and that uncertainty is what makes this discovery so exciting. Think about what this means for our understanding. For decades, we've built theoretical models of how accretion works, how magnetic fields behave, how jets form. These models have been tested against observations of many black hole systems across a wide range of masses and feeding rates. They've been remarkably successful at explaining the broad features we see. But now, with the unprecedented resolution and time coverage provided by the Event Horizon Telescope, we're seeing details that challenge these models. The magnetic field shouldn't flip this quickly. The jet base shouldn't vary on such short timescales. Yet it does, and we need to figure out why. One possibility involves something called the magnetically arrested disk state. In this configuration, magnetic fields become so strong near the black hole that they actually impede accretion. Material trying to fall encounters a magnetic pressure that pushes back, creating a kind of barrier. The black hole becomes starved of fuel, and the accretion rate drops dramatically. But magnetic fields can't hold the material back forever. Eventually, instabilities develop. The magnetic barrier breaks down, and material floods inward in what amounts to a feeding frenzy. The black hole gorges itself, the accretion disk brightens, the jet intensifies. Then the magnetic fields build up again, and the cycle repeats. If M87 transitions between different accretion states, that could explain the magnetic field changes we're observing. During a magnetically arrested phase, the field configuration would be dominated by the strong magnetic pressure near the event horizon. When the disk transitions to a more normal accretion state, the field configuration would change to reflect the properties of the inflowing material. These transitions might happen on timescales of years or decades for a supermassive black hole like M87, which would be consistent with what we're seeing. Another explanation involves precession. Just as Earth's rotation axis wobbles over long periods, creating the precession of the equinoxes, the inner accretion disk around a black hole might precess around the black hole's spin axis. If the disk is tilted relative to the black hole's equator, frame-dragging effects from the rotating black hole can cause the disk to wobble. The magnetic field, anchored in the disk, would wobble along with it. From our viewing angle on Earth, this precession might appear as a flip in the magnetic field orientation, as different parts of the disk come into view. Simulations of tilted accretion disks show that they can exhibit complex behavior. The disk might break into separate rings at different inclinations, each precessing at different rates. The magnetic field threading through these rings would twist and tangle, creating a time-varying structure that evolves in ways that are difficult to predict without detailed calculations. Some simulations suggest that the interaction between the disk and the black hole's magnetic field can even cause the black hole's spin axis itself to change direction over time, though this would require special circumstances. Stay with me, because what I'm about to reveal connects all of this to one of the biggest mysteries in astrophysics. The same techniques we're using to study magnetic fields around M87 have recently enabled scientists to detect signatures of dark matter near the black hole, and the method relies on understanding exactly how magnetic fields affect the polarization of light escaping from the accretion disk. I'll explain how in just a moment. The jets emerging from black holes represent perhaps the most spectacular consequence of accretion. These narrow beams can extend for millions of light years, punching through the interstellar and intergalactic medium, creating enormous radio lobes and heating gas across vast regions of space. The jets from the most powerful black holes affect their host galaxies and even galaxy clusters, regulating star formation and redistributing energy on cosmic scales. Astronomers call this feedback, and it's thought to be crucial for understanding how galaxies evolve. M87's jet has been studied for over a century. It was first detected in visible light photographs taken in the early 1900s, appearing as a bright spike emerging from the galaxy's nucleus. Later observations at radio wavelengths revealed the jet's true extent and showed that it contains plasma moving at speeds very close to the speed of light. The jet exhibits structure on all scales we can observe, from the inner regions just outside the event horizon to the outer lobes hundreds of thousands of light years away. Bright knots of emission appear and fade, moving downstream at apparent velocities that sometimes exceed the speed of light, a consequence of relativistic beaming rather than actual faster-than-light motion. What powers these jets remains one of the outstanding questions in astrophysics. We know magnetic fields are involved, and we know the jets tap into either the rotational energy of the black hole itself or the gravitational energy of infalling matter. But the details of how magnetic fields collimate the outflow, how particles get accelerated to such extreme energies, and what determines the jet's stability over such vast distances are still being worked out. The Event Horizon Telescope observations provide crucial constraints by allowing us to observe the base of the jet, the launching region where the physics is most extreme. Recent data from the telescope array included observations that, for the first time, detected faint emission from the jet base in the same images showing the accretion disk. This emission appears as an asymmetry in the ring of light around the black hole, brighter on one side than the other. The bright side corresponds to the direction of the jet, confirming that the jet originates from the immediate vicinity of the event horizon. The jet's orientation relative to the magnetic field structure provides clues about the launching mechanism, supporting models where twisted magnetic fields play a central role. The variability of the magnetic field might directly affect the jet's properties. If the field configuration changes, the efficiency of energy extraction could change with it. A jet powered by a magnetically arrested disk might be more powerful but less steady than a jet powered by a continuously accreting disk. The jet direction might even wobble if the disk precesses or if the magnetic field realigns. Observations of other black hole jets have revealed exactly this kind of behavior, jets that change direction over time, creating S-shaped structures in radio images. M87's jet appears relatively straight, but subtle changes in direction could occur on timescales too short for us to have noticed yet. Understanding jet physics has implications far beyond black holes themselves. Jets from supermassive black holes can influence entire galaxy clusters. As the jet plows through the surrounding gas, it creates shock waves and cavities, heating the gas and preventing it from cooling and forming stars. This feedback mechanism is thought to explain why the most massive galaxies stopped forming stars billions of years ago. The black hole, fed by gas falling into the galaxy, launches jets that heat the remaining gas, preventing further star formation. The galaxy essentially self-regulates, with the black hole acting as a thermostat. On smaller scales, jets from stellar mass black holes in binary systems can affect their companion stars. Some X-ray binary systems show periodic jets that appear to be triggered when the black hole switches between different accretion states. These microquasars, as they're called, allow us to study jet physics in systems that vary on human timescales of hours or days, rather than the years or centuries required for supermassive black holes. The physics scales differently. The same processes occur, but the energies and timescales are adjusted according to the black hole's mass. Magnetic fields in astrophysics have a way of being both crucial and frustratingly difficult to measure. Unlike gravity, which we can infer from the motion of objects, or temperature, which we can determine from spectral emission, magnetic fields require more subtle techniques to observe. Polarization measurements are our primary tool. Light becomes polarized when it interacts with magnetic fields or when it scatters off electrons. By measuring the polarization of radiation from the accretion disk, astronomers can infer the strength and orientation of the magnetic field. The Event Horizon Telescope observes at a wavelength of 1.3 millimeters in the sub-millimeter band. At this wavelength, the emission from M87's accretion disk comes primarily from from synchrotron radiation, light emitted by electrons spiraling in magnetic fields. This radiation is naturally polarized, with the polarization direction perpendicular to the magnetic field. By measuring the polarization across the image of the black hole, scientists can reconstruct the magnetic field structure in the emitting region. The recent observations showing the polarization flip mean that the magnetic field structure has changed dramatically between epochs. We need to talk about what happens when black holes collide. Not the gentle mergers of galaxies or stars, but the catastrophic union of two objects so dense that each warps space-time into a gravitational well from which nothing can escape. When two black holes spiral toward each other, they create ripples in the fabric of reality itself, gravitational waves that propagate across the universe at the speed of light, carrying away energy and angular momentum until the holes finally merge into a single, larger black hole. This process represents one of the most violent events the universe can produce. In the final moments before merger, the black holes orbit each other hundreds of times per second. They're moving at significant fractions of light speed, experiencing gravitational accelerations that would tear apart any material object. The space-time around them churns and warps, creating a dynamic geometry that shifts faster than atoms can vibrate. Then, in less than a second, the event horizons touch and coalesce. The collision releases more power than all the stars in the observable universe combined, though almost all of that power comes out as gravitational waves rather than light. Gravitational waves were predicted by Einstein over a century ago as a consequence of general relativity. Just as accelerating electric charges produce electromagnetic waves, accelerating masses should produce gravitational waves, oscillations in space-time curvature that propagate outward at light speed. But Einstein calculated that these waves would be incredibly weak. Even the most violent cosmic events would produce space-time distortions that stretch and squeeze distances by less than a trillionth of a percent. He doubted they would ever be detected. Einstein underestimated human ingenuity. In late 2015, the Laser Interferometer Gravitational Wave Observatory, known as LIGO, detected gravitational waves for the first time. The signal came from two black holes, each about 30 times the mass of the Sun, spiraling together and merging more than 1 billion light-years away. The waves stretched and compressed LIGO's 4-kilometer arms by a distance smaller than the width of a proton, but the instruments were sensitive enough to measure it. That detection opened an entirely new window on the universe and earned its architects the Nobel Prize in Physics. Since that first detection, LIGO and its partner observatory Virgo have detected dozens of black hole mergers. Each one provides unique information about the masses, spins, and orbital parameters of the merging objects. Recently, they recorded what may be the most significant detection yet, a merger that produced the clearest signal ever observed, allowing scientists to measure the properties of the resulting black hole with unprecedented precision. The merger involved two black holes weighing 65 and 95 times the mass of the Sun. These are at the upper end of what we expect from stellar collapse, approaching the boundary where pair instability supernovae should prevent black hole formation. Their collision produced a final black hole weighing about 150 solar masses. The missing 10 solar masses converted entirely into gravitational wave energy in the final fraction of a second, radiating away as ripples in spacetime. The signal was so clear that scientists could measure not just the masses, but also the spins of the black holes before and after merger. This data tests predictions from general relativity in the strongest gravitational fields we can observe. The theory passed with flying colors. The final black hole's mass and spin matched predictions to within the measurement uncertainties. The quasi-normal modes, the characteristic ringing of space-time as the merged black hole settles down, appeared exactly where Einstein's equations said they should be. But something unexpected also happened. After the merger, the resulting black hole received a kick, a recoil velocity of more than 1,200 kilometers per second. This kick results from the asymmetric emission of gravitational waves during the collision. If the two black holes have different masses, or their spins are misaligned, the gravitational wave emission carries more momentum in one direction than another. Conservation of momentum means the merged black hole must recoil in the opposite direction. 1,200 kilometers per second might not sound impressive compared to the near-light speed orbital velocities just before merger, but it's fast enough to have dramatic consequences. That velocity exceeds the escape velocity from most galaxies. A black hole kicked at this speed would be ejected from its host galaxy entirely, wandering through intergalactic space as a rogue object. Over cosmic time, such kicks might explain why some galaxies lack the central supermassive black holes we expect to find. Scientists have even translated the gravitational wave signal into sound, creating an audio representation of what the merger sounds like. It begins with a rising chirp as the black holes spiral together, their orbital frequency increasing as they get closer. Then comes a sharp tone as the event horizons merge, followed by a decaying ring down as the final black hole settles into a stable state. The entire sequence lasts less than a second, compressed from the hours or years of inspiral that preceded it. This particular merger confirmed predictions made by both Einstein and Stephen Hawking. Einstein's general relativity predicted the gravitational wave signal's shape and strength. Hawking's area theorem predicted that the event horizon's total surface area must increase during the merger. Despite the violent collision, despite the complexity of merging curved spacetimes, the final black hole's surface area exceeded the sum of the two original horizons' areas. Information might be lost when things fall into black holes, but at least area increases, providing a kind of cosmic bookkeeping that prevents certain paradoxes. The study of merging black holes has revealed something unexpected about the black hole population in our universe. The masses of black holes detected by LIGO cluster around 30 to 40 solar masses, heavier than most black holes formed from stellar collapse in our galaxy. Either the stars that form black holes this massive are more common than we thought, or many of the black holes we're detecting formed through previous mergers. A black hole born from stellar collapse might merge with another, creating a second-generation black hole. That could merge again, producing third-generation black holes, and so on. This hierarchical merging might help explain how supermassive black holes grow. Starting from stellar mass seeds, repeated mergers over billions of years could build up the enormous masses we observe in galactic centers. But the timescales present a challenge. Mergers don't happen quickly. Black holes in a galaxy need to find each other, lose enough orbital energy to spiral together, and finally coalesce. Each step takes time, and we're still working out whether this process alone can produce the supermassive black holes we see in the early universe. Now here's where things get really interesting, and I promised I'd connect this back to the magnetic field changes in M87. Scientists recently discovered that gravitational wave detections can be combined with electromagnetic observations to probe environments around black holes in unprecedented detail. When black holes merge inside gas clouds or accretion disks, the merger can produce not just gravitational waves, but also light. These multi-messenger events provide far more information than either signal alone. Imagine two supermassive black holes orbiting each other at the center of a galaxy. Their combined gravity has cleared out much of the surrounding gas, creating a gap in the galactic disk. As they spiral closer, tidal forces and orbital dynamics push gas into the gap, where it gets superheated by friction and radiates brightly. The binary black hole system appears as a periodic X-ray source, flashing each time the holes swing past each other. Then, as the merger approaches, the emission might spike dramatically as the holes plunge through any remaining gas. The gravitational waves from such a merger would be detectable by future space-based detectors like LISA, while the electromagnetic counterpart could be observed by traditional telescopes. This brings us to a discovery that happened just recently, the first ever image of two black holes orbiting each other. Astronomers, using a combination of radio telescope observations, resolved two distinct black holes in a single system. The primary black hole weighs 18 billion solar masses, one of the most massive known. The secondary weighs 150 million solar masses. Despite the enormous size difference, both are visible in the images because they're surrounded by their own accretion disks, each glowing with the heat of infalling matter. These black holes orbit each other every 12 years or so, bound together by gravity, but still separated by several light months. That separation might seem large, but on cosmic scales it's incredibly close. The system shows periodic brightness variations as the black holes swing past each other, compressing and heating the gas between them. Based on their current orbital parameters, astronomers predict they'll merge in about 10,000 years, the blink of an eye in cosmic terms, though far too long for any human to witness. The existence of such binary systems has important implications. Many galaxies show evidence of past mergers with other galaxies. When galaxies merge, their central black holes should eventually sink to the combined galaxy's center and form a binary. But actually getting the black holes close enough to merge requires removing an enormous amount of orbital energy. Gas friction and interactions with stars can do this initially, but once the black holes get within a few light years of each other, these processes become inefficient. This is called the final parsec problem, and it's one reason some scientists worried that supermassive black hole mergers might be rare or slow. Recent observations suggest the problem might solve itself in gas-rich environments. If the binary black holes are surrounded by a circumbinary disk, a disk of gas orbiting both holes, the gravitational torques between the disk and the binary can continue extracting energy and angular momentum, driving the holes together. The disk might even channel gas onto the black holes, causing them to grow as they spiral inward. Some simulations show that this process can overcome the final parsec problem efficiently, meaning supermassive black hole mergers should be common in the universe. Every black hole merger we detect teaches us something new. Some mergers show evidence for precessing spins, where the black hole's rotation axes wobble as they orbit. Others show nearly aligned spins, suggesting the black holes formed together from the same gas cloud. Still others show anti-aligned spins, where one hole rotates in the opposite direction, indicating they came together by chance rather than forming as a pair. These spin configurations encode the history of how the black holes formed and evolved. One particularly intriguing possibility is that some mergers involve black holes with highly eccentric orbits. Most detections so far show relatively circular orbits just before merger, as expected when the holes spiral together gradually. But if black holes can form through other mechanisms, direct collapse in dense star clusters, for instance, they might end up in eccentric orbits. An eccentric merger would produce a different gravitational wave signature, one that's harder to detect but potentially reveals different physics. The power of multi-messenger astronomy became clear when LIGO detected gravitational waves from a neutron-star merger. Within seconds, telescopes around the world turned to observe the source. They detected a kilonova, a brilliant optical and infrared transient powered by radioactive decay of heavy elements synthesized in the merger. X-ray and radio observations followed, tracking the evolution of the expanding debris. This single event confirmed that neutron star mergers produce heavy elements like gold and platinum, solving a decades-old mystery about the origin of the heaviest elements in the periodic table. Black hole mergers generally produce fainter electromagnetic counterparts because black holes don't have surfaces to collide. Most of the energy goes into gravitational waves rather than light. But if the merger happens inside a dense gas cloud or an accretion disk, the resulting disturbance can produce detectable emission. Scientists are actively searching for these counterparts, hoping to catch a supermassive black hole merger in progress. Such an event would test our understanding of accretion physics under the most extreme conditions imaginable. The kicked black hole I mentioned earlier raises fascinating questions. What happens to a black hole wandering through intergalactic space? If it passes through gas clouds, it might accrete some material and briefly light up as an active galactic nucleus. But most of intergalactic space is nearly empty, so such encounters would be rare. The black hole would spend most of its existence as a dark, invisible object, detectable only through its gravitational influence on anything passing nearby. Could Earth ever encounter a wandering black hole? The probability is vanishingly small. Space is vast, and even with potentially millions of rogue black holes in every galaxy cluster, the average distance between objects remains enormous. A stellar mass black hole would need to pass within a few light years of the solar system to have any noticeable effect, and the odds of that happening in the remaining lifetime of the Sun are essentially zero. Even if it did happen, we'd have plenty of warning. A massive object approaching the solar system would perturb the orbits of distant comets and asteroids long before it came close enough to endanger Earth. For decades after Einstein predicted their existence, black holes remained purely theoretical. Astronomers suspected they existed, but proving it required finding objects that matched the extreme properties the mathematics demanded. The breakthrough came from an unexpected direction. In the late 1960s, satellites designed to detect nuclear weapons tests in space started picking up bursts of X-rays coming from the cosmos. These weren't bombs, they were celestial objects radiating enormous amounts of high-energy light. One source in particular caught astronomers' attention. Cygnus X1, an intense X-ray emitter in the constellation Cygnus, appeared to be orbiting a blue supergiant star. By measuring how the star wobbled, scientists calculated the invisible companion's mass at around 15 times the Sun. That mass exceeded the theoretical limit for neutron stars, leaving only one possibility. Cygnus X1 had to be a black hole, the first one ever identified with reasonable confidence. Stephen Hawking famously bet against this conclusion in the 1970s, wagering that Cygnus X1 would turn out to be something else. He eventually conceded the bet, acknowledging that the evidence had become overwhelming. The X-rays coming from Cygnus X1 don't emerge from the black hole itself. They come from an accretion disk formed by gas pulled off the companion star. As this gas spirals inward, friction heats it to tens of millions of degrees, hot enough to radiate in X-rays. The system acts like a cosmic particle accelerator, converting gravitational potential energy into radiation with terrifying efficiency. About 10% of the infalling mass energy can be radiated away, far more efficient than nuclear fusion, which converts less than 1% of mass into energy. This discovery opened the floodgates. Astronomers found similar systems throughout our galaxy and beyond. Each X-ray binary told a similar story. A compact object, either a neutron star or black hole, feeding on a companion star and announcing its presence through high-energy radiation. Some systems show periodic outbursts, brightening and fading on timescales of weeks or months as the accretion rate varies. Others remain relatively steady, continuously devouring material from their unlucky partners. The relationship between a black hole and its companion star can last millions of years, but it always ends badly for the star. The black hole hole gradually strips away the star's outer layers, growing more massive while the star shrinks. Eventually, the star might be reduced to a white dwarf or completely consumed. The black hole, now better fed and more massive, continues its existence, potentially finding new companions through dynamical interactions in dense stellar environments. Binary systems containing black holes have revealed unexpected diversity. Some pairs orbit each other in mere hours, locked in a gravitational embrace so tight that the stars are distorted into egg shapes by tidal forces. Others maintain more distant relationships, orbiting over days or weeks. The orbital parameters depend on how the system formed, whether the black hole's progenitor star exploded as a supernova while bound to its companion, or whether two previously independent objects were captured by each other's gravity. Supernova explosions that create black holes can be asymmetric, giving the newly formed black hole a kick velocity that sometimes exceeds the orbital speed of the binary. When this happens, the system gets disrupted, and both objects go their separate ways. Astronomers have found runaway stars racing through space at hundreds of kilometers per second, likely flung away when their companion exploded and formed a black hole. These cosmic refugees carry with them the story of their violent pasts, written in their peculiar velocities and chemical compositions. Meanwhile, at the centers of galaxies, supermassive black holes were revealing their presence through different signatures. Quasars, those incredibly bright objects discovered in the early 1960s, puzzled astronomers for years. They appeared as point sources in the sky, looking like stars, but their spectra showed enormous redshifts indicating they were billions of light-years away. To be visible at such distances, quasars had to be outputting the energy equivalent of hundreds or thousands of galaxies, while occupying a region smaller than our solar system. The only explanation that made sense involved supermassive black holes. A black hole weighing billions of solar masses, surrounded by a massive accretion disk, could produce the observed luminosities. The disk would shine so brightly that it would outshine all the stars in the host galaxy combined. From our perspective, across billions of light-years, we'd see only the brilliant point of light from the active nucleus, not the dimmer stars surrounding it. Quasars, astronomers realized, were the most extreme examples of active galactic nuclei, powered by supermassive black holes gorging on unprecedented amounts of gas. As telescopes improved, astronomers discovered that most large galaxies harbor supermassive black holes at their centers, even when those black holes aren't actively feeding. Our own Milky Way contains a relatively quiet specimen called Sagittarius A star, weighing about 4 million solar masses. We can't see it directly in visible light because intervening dust blocks our view, but radio and infrared observations reveal stars orbiting the galactic center at speeds exceeding 5,000 kilometers per second. Only a supermassive black hole could hold stars in such tight, fast orbits. One star in particular, designated S2, completes its orbit around Sagittarius A star every 16 years. At its closest approach, this star ventures within just 17 light hours of the event horizon, traveling at nearly 3% of light speed. Tracking S2's orbit over multiple years has allowed astronomers to test general relativity in the strong field regime. The star's orbit precesses slightly with each passage, just as Einstein's equations predict. Mercury's orbit around the Sun shows similar precession, but S2's effect is far more pronounced because it experiences much stronger gravitational fields. The connection between galaxies and their central black holes runs deeper than simple cohabitation. Observations reveal a tight correlation between a galaxy's bulge mass and its central black hole mass. More massive galaxies have more massive black holes, with the black hole typically weighing about 1/5 of 1% of the bulge mass. This relationship suggests that black holes and galaxies grow together, influencing each other's evolution through cosmic time. When a supermassive black hole feeds actively, it doesn't just grow, it also affects its surroundings through powerful feedback mechanisms. The radiation pressure from the accretion disk can drive winds that sweep gas out of the galactic nucleus, regulating star formation. The jets launched by the black hole can heat gas on much larger scales, preventing it from cooling and collapsing to form new stars. This feedback might explain why the most massive galaxies appear to have stopped forming stars billions of years ago, despite containing enormous amounts of gas. Galaxy mergers trigger some of the most dramatic black hole activity. When two galaxies collide, their gas clouds crash together, lose angular momentum, and funnel toward the center. This gas glut feeds the central black holes, potentially triggering quasar activity. The merging galaxies' black holes themselves themselves sink toward the combined center, eventually forming a binary that will itself merge after losing enough energy to gravitational wave emission. The whole process transforms the galaxies, redistributing stars and gas while growing the central black hole to enormous size. Astronomers classify active galactic nuclei into several types based on their observed properties. Seyfert galaxies show bright nuclei with strong emission lines, indicating energetic processes near the central black hole. Radio galaxies produce powerful jets visible across millions of light-years. Blazars are extreme cases where we're looking nearly straight down the jet, seeing radiation beamed toward us by relativistic effects. Quasars represent the most luminous examples, visible across cosmic distances. Yet all these phenomena likely arise from the same underlying physics, a supermassive black hole accreting matter and converting gravitational energy into radiation and kinetic energy. The study of active galactic nuclei has revealed that black hole feeding is episodic rather than continuous. A black hole might spend most of its time relatively quiet, accreting at low rates and producing little radiation. Then something, perhaps a galaxy merger, perhaps a star wandering too close and getting tidally disrupted, delivers a fresh supply of gas to the nucleus. The black hole lights up, shining as a quasar or active galaxy for perhaps a few million years before exhausting the gas supply and returning to quiescence. This episodic nature means that observations capture black holes in various states. Some are in the midst of active feeding episodes, blazing across the cosmos. Others finished their last meal millions of years ago and now sit quietly, revealed only through the orbital motions of nearby stars. Still others might be ramping up, just beginning a new feeding phase as gas makes its way to the nucleus. Understanding this cycle has been crucial for piecing together how black holes grow from the relatively small seeds that formed in the early universe to the billions of solar mass behemoths we observe today. Recent work has connected black hole activity to the large-scale structure of the universe. Galaxies don't exist in isolation. They cluster together, connected by filaments of dark matter that channel gas along cosmic web structures. Gas flowing along these filaments can feed central black holes, triggering activity that might be synchronized across multiple galaxies in a cluster. The radiation and jets from active black holes can then affect the entire cluster environment, heating the intergalactic medium and regulating star formation on scales encompassing millions of light-years. This brings us to one of the most profound mysteries in astrophysics, and the connection I promised earlier. Dark matter makes up roughly 85% of all matter in the universe, yet we've never directly detected a single dark matter particle. We know it exists because of its gravitational effects. Galaxies rotate too fast to be held together by visible matter alone. Galaxy clusters contain far more mass than we can account for in stars and gas, and gravitational lensing reveals invisible mass-bending light from distant sources. Scientists have proposed numerous candidates for what dark matter might be. Weakly interacting massive particles remain popular, though decades of experiments have failed to detect them. Primordial black holes formed in the early universe represent another possibility, though observations constrain how many could exist. Axions, sterile neutrinos, and more exotic options all have their proponents. Despite enormous effort, dark matter's identity remains unknown. Here's where the recent black hole observations become revolutionary. Scientists have discovered that magnetic field measurements around supermassive black holes can reveal dark matter's presence. The technique relies on how dark matter particles interact with the intense electromagnetic fields near the event horizon. Even if dark matter particles interact only weakly with normal matter, they still respond to gravity. Near a black hole, dark matter should form a dense halo, with particles orbiting in the intense gravitational field. This dark matter halo would affect the accretion disk's behavior. Interactions between dark matter particles and normal matter, however weak, could transfer energy and momentum. More importantly, the gravitational effect of the dark matter halo would subtly modify the disk's structure and the magnetic field configuration. These modifications would appear as specific signatures in the polarization patterns of light from the accretion disk. The Event Horizon Telescope observations of M87 have detected exactly these kinds of anomalies. The polarization data shows features that can't be explained by ordinary matter alone. The magnetic field structure includes components that require additional mass in the immediate vicinity of the black hole, mass that doesn't radiate and doesn't interact electromagnetically. The most likely explanation is a dense dark matter halo concentrated by the black hole's immense gravity. If dark matter concentrates around black holes, then every supermassive black hole in the universe sits at the center of an invisible halo containing more mass than millions of suns. This dark matter doesn't emit light, doesn't absorb light, and barely interacts with ordinary matter. Yet its gravitational influence shapes the accretion disk, affects the magnetic field structure, and leaves subtle fingerprints in the polarization of escaping radiation. The recent observations from the Event Horizon Telescope have given us our first glimpses of these fingerprints. The implications extend far beyond detecting dark matter. If we can measure dark matter distributions around black holes, we gain a new tool for understanding galaxy evolution. Dark matter halos guide the flow of gas into galaxies, channeling material that eventually feeds central black holes and forms stars. The relationship between dark matter, normal matter, and black hole growth has shaped cosmic structure for billions of years. Now we can finally observe this process directly, watching how invisible matter concentrates in the most extreme gravitational environments in the universe. Scientists working with the Event Horizon Telescope data have identified specific anomalies that point toward dark matter. The brightness distribution in the ring around M87 shows asymmetries that ordinary matter alone can't explain. The magnetic field orientation includes features requiring additional gravitational sources near the event horizon. Computer simulations that include dark matter halos reproduce these observations far better than simulations with ordinary matter only. The evidence isn't conclusive yet, but it's compelling enough that multiple research groups are pursuing this interpretation. This detection method opens possibilities for studying dark matter properties we couldn't access before. Laboratory experiments searching for dark matter particles rely on detecting rare interactions between dark matter and ordinary atomic nuclei. Those experiments have become incredibly sensitive, yet they've found nothing. The problem might be that dark matter interacts even more weakly than we thought, or perhaps it's made of something entirely different from what we've been looking for. Black holes offer an alternative approach. Their intense gravity concentrates dark matter, regardless of how weakly it interacts, creating dense halos we can study through gravitational effects alone. The connection between black holes and fundamental physics runs deeper still. When Stephen Hawking showed that black holes should emit radiation through quantum mechanical effects, he uncovered a profound puzzle that physicists still grapple with today. Hawking radiation arises from quantum fluctuations at the event horizon. Virtual particle pairs constantly pop into existence throughout space, normally annihilating each other almost immediately. But near the event horizon, one particle can fall into the black hole while the other escapes. From an outside perspective, the black hole appears to emit radiation with a temperature inversely proportional to its mass. For a stellar mass black hole, this temperature is incredibly small, far colder than the cosmic microwave background radiation permeating space. The black hole absorbs more radiation from its surroundings than it emits through Hawking radiation. But as the universe expands and cools, and assuming the black hole doesn't feed on additional matter, there will eventually come a time when Hawking radiation dominates. The black hole begins to lose mass, shrinking gradually over timescales that dwarf the current age of the universe. As a black hole shrinks, its temperature increases, the process accelerates, with the black hole radiating faster and faster as it gets smaller and hotter. In the final moments, the black hole essentially explodes in a burst of high-energy particles and radiation. For a solar mass black hole, this process would take about 10 to the 67th years, a time span so vast it makes the current age of the universe seem like an eye blink. Supermassive black holes would take even longer, surviving until the cosmos is unimaginably old and cold. Hawking radiation introduces what physicists call the information paradox. Quantum mechanics insists that information cannot be destroyed. The quantum state of a system determines its future evolution, and you should always be able to reconstruct the past from complete knowledge of the present. But if a black hole evaporates completely through Hawking radiation, where does the information about everything that fell in go? The radiation appears thermal, carrying no information about what created it. A black hole formed from collapsed stars would produce the same radiation as one formed from pure hydrogen gas, violating quantum mechanics' fundamental principle. Hawking initially argued that information really does get destroyed, that black holes represent an exception to quantum mechanical conservation laws. This suggestion horrified many physicists, triggering decades of debate and research. Some proposed that information gets encoded in subtle correlations within the Hawking radiation, imperceptible unless you could collect and analyze every single emitted particle. Others suggested the information escapes through wormholes or gets preserved in hypothetical remnants left behind when black holes finish evaporating. Recent theoretical work suggests a resolution involving what physicists call black hole complementarity. From the perspective of someone falling into a black hole, they cross the event horizon smoothly and continue falling toward the singularity. Information seems to be lost, but from the perspective of an outside observer, infalling matter never quite reaches the horizon. It appears to spread across the horizon's surface, getting scrambled and eventually re-emitted as Hawking radiation. Both perspectives are valid within their respective reference frames, and information gets preserved in the outside observer's perspective. This resolution relies on heavy mathematics involving holography and quantum entanglement, concepts at the frontier of theoretical physics. The holographic principle suggests that all the information about a volume of space can be encoded on its boundary, much like a hologram encodes three-dimensional information in a two-dimensional surface. Applied to black holes, this means everything that falls in gets encoded on the event horizon, available to be extracted from the Hawking radiation emitted over cosmic timescales. Testing these ideas experimentally presents enormous challenges. We can't observe Hawking radiation from real black holes. It's far too weak to detect above the background noise of the universe. We can't create black holes in laboratories to study their quantum properties. Instead, physicists rely on analogs, systems that mimic aspects of black hole physics in controllable settings. Sonic black holes in superfluid helium, optical black holes in flowing light, and simulations in other quantum systems have all provided insights, though none perfectly replicate the extreme conditions around real event horizons. The information paradox connects to another deep mystery, the nature of space-time at the smallest scales. General relativity treats space-time as a smooth continuum that can be curved and warped. Quantum mechanics describes particles and fields evolving in fixed space-time backgrounds. These two pillars of modern physics work brilliantly in their respective domains, but refuse to combine into a consistent theory of quantum gravity. Near the singularity at a black hole's center, both quantum effects and strong gravity become important. The classical picture of a point of infinite density breaks down. Quantum fluctuations of spacetime itself should become significant, possibly preventing the formation of a true singularity. String theory, loop quantum gravity, and other approaches to quantum gravity all predict modifications to the black hole interior, but we lack experimental evidence to distinguish between competing theories. One intriguing possibility is that black holes might not have singularities at all. Instead, quantum gravitational effects might halt the collapse before a singularity forms, creating what some theorists call a black hole firewall, or replacing the interior with something entirely different. Another idea proposes that black holes could be wormholes connecting to other regions of spacetime, or even other universes. Material falling in wouldn't hit a singularity, but would emerge somewhere else, though the connection would be traversable only in one direction. The recent black hole observations are testing general relativity in unprecedented detail. Einstein's equations make specific predictions about space-time curvature around black holes, the shapes of event horizons, and how light bends in strong gravitational fields. The Event Horizon Telescope images confirm these predictions with remarkable precision. The shadow of M87's black hole matches the size and shape Einstein's theory requires. The ring of light shows the gravitational lensing effects predicted by general relativity. No deviations have been detected despite the exquisite measurements. Similarly, the gravitational wave detections from merging black holes test general relativity's predictions for how spacetime itself oscillates and radiates. The waveforms observed by LIGO and Virgo match Einstein's equations across a wide range of masses and orbital configurations. The final ringdown as merged black holes settle into stable states produces frequencies that depend only on the final mass and spin, exactly as predicted. Alternative theories of gravity that predict different ringdown frequencies or different gravitational wave polarizations have been ruled out by these observations. Yet physicists know that general relativity can't be the complete story. The theory predicts its own breakdown at singularities and doesn't incorporate quantum mechanics. Somewhere in the extreme environments around black holes, effects beyond general relativity must appear. Finding those effects has become a holy grail of observational astronomy. Every new black hole observation, every improvement in measurement precision, brings us closer to detecting the first hints of physics beyond Einstein. The masses of black holes detected through gravitational waves have revealed surprises. Some mergers involve black holes heavier than expected from stellar evolution models. Others show evidence for intermediate mass black holes, a population we've struggled to find through other methods. The distribution of masses and spins provides clues about how black holes form and evolve, testing models of stellar evolution and gravitational dynamics in dense stellar environments. One fascinating pattern involves the mass gap between neutron stars and black holes. Neutron stars top out at about 2 to 2.5 solar masses. Beyond that, gravity overcomes neutron degeneracy pressure, and collapse to a black hole becomes inevitable. The lightest stellar mass black holes should therefore weigh around 3 solar masses, but observations show a gap, with few compact objects between 2 and 5 solar masses. Recent gravitational wave detections have started filling this gap, finding objects whose masses fall in the previously empty range. These gap objects raise questions about their nature. Are they the heaviest possible neutron stars, compressed to the point where exotic physics in their cores becomes important? Are they the lightest black holes, perhaps formed through unusual supernova mechanisms? Or might they be something entirely different, compact objects whose equation of state differs from both neutron stars and black holes? Each new detection constrains the possibilities, gradually revealing the full spectrum of dense matter states the universe can produce. The spins of black holes tell their own story. Black holes can rotate, with the rotation rate characterized by a dimensionless spin parameter ranging from 0 for non-rotating holes to 1 for maximally rotating Kerr black holes. Stellar collapse should produce black holes with moderate spins, depending on the rotation of the progenitor star's core. Black holes formed through mergers might have higher or lower spins depending on the orbital configuration. The observed spin distribution includes both slowly rotating and rapidly rotating black holes, suggesting multiple formation channels contribute to the population. Measuring black hole spins from gravitational waves is challenging but possible. The waves encode information about how the black hole's spins affect their orbital motion and the final merger. Recently detected events have provided spin measurements precise enough to distinguish between formation scenarios. Some black holes show nearly aligned spins, suggesting they formed together or evolved in an aligned configuration. Others show misaligned or even anti-aligned spins, indicating they came together through dynamical capture rather than co-evolution. The universe announces its most violent moments not with light, but with a tremor that rolls through space-time itself. Tonight we're going to follow that tremor to its source and watch two black holes complete a dance that began long before any stars like ours were born. Imagine a pair of invisible giants circling each other, faster and tighter with every lap. Their gravity braids space into a whirlpool. Their motion pumps energy into the fabric of the cosmos. And then, in a breath, horizons touch, surfaces fuse, and a single, larger shadow takes the stage while the universe rings like a bell. Listen to that ring. It starts quietly, a low ripple, almost indistinguishable from silence. As the black holes spiral inward, the pitch rises, the rhythm quickens, and the power climbs to a peak that outshines entire galaxies. Only not in light, in pure geometry. When the two horizons join, the roar becomes a single note, a clean, dying tone as the newborn black hole settles and the distortions decay. That ring carries a signature. Hidden in its shape is a precise record of the masses, spins, and alignment of the pair that came before and of the remnant that remains. Decode the pattern, and you read a birth certificate written by gravity. This is more than spectacle. It's a test bench for the deepest ideas in physics. The spiral and the ring down are not random noise. They match mathematical predictions made long before any detector ever heard a whisper from the sky. Each clear signal tightens the screws on our theories. If space-time behaved differently in the strongest fields, that ring would betray it with a single wrong note. It hasn't, not yet. The melody has been faithful to the score. But the more carefully we listen, the more subtle harmonics we can hear, and some of those harmonics might be the first clues of new physics waiting beyond our current reach. Now picture where these collisions happen. Sometimes they unfold in quiet corners of galaxies, in sparse halos where gas is thin and light is scarce. Sometimes they happen in crowded star clusters, where gravity is a social force that nudges strangers together until orbits tangle and pairs form by chance. A black hole can trade partners, capture a neighbor, or collide in chaotic three-body encounters that throw one object out as another pair tightens to a fatal embrace. That chaos leaves fingerprints, misaligned spins, eccentric orbits, unusual mass ratios. When the wave washes over us, we can tell a quiet courtship from a violent brawl by the patterns embedded in the chirp. There's another route. Two massive stars are born together, live fast and die close. Each collapse leaves behind a compact object. If the system survives both deaths, and many do, the pair slowly spirals together under the steady drain of gravitational radiation. Those systems tend to keep their spins aligned with the orbit. Their signal rises smoothly and cleanly, a polished crescendo. By comparing the waveforms from event to event, we can sort family histories, arranged marriages forged at birth, and wild romances in the densest neighborhoods of the universe. Environment matters. If gas and dust crowd the stage, a merger can shine as well as sing. Shocks heat the surrounding medium. Magnetic fields twist, reconnect, and flash. A merger inside a disk near a supermassive black hole can stir that disk and crank up its brightness for weeks. Most of the time, the light is faint or short-lived, but every time we catch even a hint of glow alongside the gravitational wave, we get context. Location within a galaxy, the kind of neighborhood, and the chemistry of the aftermath. Gravity tells us what happened. Light tells us where and in what company. Even without light, The waves alone can be startlingly informative. Sometimes the final black hole recoils. Picture two skaters colliding mid-spin. If their motions don't cancel perfectly, the result shoots off across the ice. In space-time, an asymmetric blast of gravitational radiation carries momentum one way, so the remnant kicks the other way. That kick can be gentle, or it can be a cannon shot fast enough to throw the new black hole out of the galaxy that birthed it. A single kick like that can rearrange a galaxy's future. A central engine unplugged, a long era of star formation no longer throttled by a ravenous core, a halo left to cool and change course. The roster of masses we've measured is a story in itself. For years, observations of stellar deaths suggested black holes would cluster at certain sizes, leaving a gap between the heaviest neutron stars and the lightest black holes. The waves filled that gap with real objects. Some are barely past the threshold where matter can no longer resist collapse. Others are so heavy they strain our models of how stars explode. The most massive mergers we've seen hint at a ladder of ancestry. A black hole born from a collision merges again and again, building mass like a snowball rolling downhill. That ladder climbs toward the realm of intermediate mass black holes, the long-suspected middle children between stellar corpses and galactic giants. Why should you care about ladders and gaps and kicks? Because they explain what we are likely to witness next. If black holes can grow by repeated mergers in dense clusters, then those clusters are factories quietly feeding the universe a supply of heavier and heavier objects. If gas disks near supermassive black holes nurture pairs and shepherd them inward, then galactic cores are farms where mergers ripen. Each factory and each farm has its own rhythm, and the overall cosmic rate of mergers, the number we hear per month, per week, per day, tells us which process dominates. That rate has been climbing as our ears sharpen. With every improvement in sensitivity, once silent events cross the threshold into audibility. Think about how improbable this listening is. We are measuring changes in distance smaller than a fraction of a proton over arms many kilometers long, while the ground itself shakes with trucks, wind, and tiny earthquakes. To beat that noise, the instruments suspend mirrors on glass threads, shine lasers stabilized to absurd precision, and cancel disturbances with algorithms tuned to the physical world like musical instruments tuned to a key. The data that arrives is messy, but buried in it is a heartbeat from halfway across the universe. Pull it out, and you've turned the planet into an ear. The payoff isn't just physics textbooks. Technology born from this effort, lasers, coatings, vibration isolation, quantum noise control, spills into medicine, communications, and sensing. A project that began as an attempt to hear colliding black holes ends up improving how we image tissue, how we stabilize clocks, how we navigate. Curiosity is a practical force disguised as wonder. There is another horizon ahead. The waves we've heard so far come from relatively small black holes compared to the monsters in galactic centers. Their songs are high notes. To hear the slow, deep voices of supermassive pairs as they circle over years, we need observatories in space. Put detectors on separate spacecraft, send them flying in a triangle millions of kilometers apart, and let them track each other by laser. The low notes will ring out, the stately two steps of giants nearing their final embrace, the rumble of galaxies stitching themselves together, and perhaps the chorus of a background hum from countless distant pairs singing at once. When that happens, we'll stitch together a complete symphony, high notes from stellar remnants, low notes from galactic rulers, and the rare harmonies when both worlds interact. We will watch a supermassive pair carve a path through a circumbinary disk, see the flow of gas modulate the wave, and pinpoint the galaxy harboring the duo. We will know not just that a merger happened, but which galaxy changed forever because of it. And when light flares in step with the wave, we'll trace the detailed physics of shocks, magnetic reconnection, and particle acceleration in real time. All of this loops back to the puzzle that first pulled us into this documentary. Black holes are more dynamic than we thought. If a magnetic field can flip near a horizon on human timescales, if jets can pulse and precess, if disks can choke on their own fields, and then snap open in a burst, then the engines that power some of the brightest phenomena in the universe are not slow and stately. They are alive with instabilities and transitions. Mergers pour fuel onto that fire. The final plunge can torque a disk, tilt a jet, or light a flare that arcs across the spectrum. Catching those moments requires coordination, patience, and a willingness to stare at noise until it reveals a pattern. Take a breath and imagine the last second of a merger, as if you could stand safely nearby. The orbit blurs into a single swirl. Space stretches and squeezes rhythmically. The silhouettes reach out and fuse. There's no shockwave in the ordinary sense, no sound to carry through a vacuum. But geometry itself shakes. The newborn horizon quivers, then smooths, and in that smoothing is the story we decode. A mass, a spin, a direction it's likely to travel. The universe has moved a piece on the board. We can follow that piece. If the remnant races away, it leaves a wake through any gas it crosses, heating it faintly. If it stays anchored at a galaxy's core, it may reignite an old jet or start a new one. In a cluster, the jet may carve out cavities in hot plasma, inflating bubbles larger than entire galaxies. Over time, those cavities rise, cool, and collapse, setting off cycles of heating and cooling that throttle how new stars switch on. A single collision, magnified by feedback, can set the thermostat for an entire city of galaxies. There's poetry in the statistics. Each detection is a line. A year of listening is a stanza. A decade becomes a chapter. With enough chapters, we see arcs, birthplaces shifting from quiet fields to crowded towns, masses sliding upward as hierarchical growth takes hold, spins trending toward disorder as dynamical encounters mix the population. Patterns like these don't just tell us about black holes, they tell us how the universe builds complexity from gravity alone. We've come far in a short time. Yesterday, the idea of hearing space-time was daring. Today, it is routine enough that alerts go out in near real time, and telescopes pivot to search for light. Tomorrow, detectors on the ground and in space will join forces, spanning octaves from high to low and back again. With that range, we will watch intermediates emerge from clusters, trace the last orbits of supermassives in merging galaxies, and perhaps stumble upon something that refuses to fit. A waveform with a kink that shouldn't be there, a ringdown with a note too sharp, a post-merger echo that hints at exotic structure where smooth geometry ought to be. Hold on to that possibility. Discovery rarely announces itself with a fanfare. It hides in a residual, a leftover after a model fits, a deviation that survives every sanity check. If such a deviation persists, it will force a reckoning with the way we think about horizons, information, and the quantum ingredients of space-time. That is why this field is so electrifying. Every new event is both confirmation and question, both a proof and a dare to look closer. Stay with this journey. In the next movement, we will leave the realm of collisions and turn our attention back to the engines that rule galactic centers. We will put the pieces together, how magnetic fields flip, how jets ignite, how disks choke and breathe, and how the newest images and the freshest waves combine into a single, coherent picture of black holes as living systems. The promise from the beginning was to explain the impossible behavior we've just witnessed. By the end, that promise will be kept. The cosmos speaks in waves beyond light and sound, ripple through the fabric of space-time, heralding the gravest cosmic dances. Imagine two titanic black holes locked in a spiraling embrace, circling faster and faster under their mutual gravitational pull, their black horizons drawing ever closer. Each orbit distorts space-time, sending gravitational waves outward across the universe like the faintest heartbeat of a distant giant. When these horizons finally touch and merge, the energy unleashed surpasses that of all the stars in visible space combined. This violent union generates a burst of gravitational waves that we can now detect with extraordinary precision. This cosmic symphony was first directly heard only recently, a validation of Einstein's profound predictions a century earlier. The detection shattered expectations, measuring distortions smaller than a fraction of a proton across kilometers-long detectors on Earth. Each detection improves our understanding, refining models of gravity, and testing fundamental physics. Gravitational wave observatories now regularly capture dozens of black hole mergers each year, revealing an unexpected diversity in their masses and spins. One of the most striking discoveries involved a merger producing a black hole much larger than expected, weighing hundreds of solar masses, a mass range previously deemed forbidden by standard stellar evolution models. This challenges existing theories and suggests new formation paths, possibly involving repeated mergers building black holes step by step. The energetic ripples from this event exhibited exquisite clarity, allowing scientists to probe and confirm fundamental aspects of black hole physics, including Stephen Hawking's area theorem. This theorem asserts that black hole horizons grow during such mergers, a cosmic bookkeeping preventing paradoxes. Recent observations have also revealed that the resulting black hole receives a recoil or kick at high velocities due to asymmetries in gravitational wave emission during the merger. This kick can expel black holes from their host galaxies, sending them wandering through intergalactic space. This phenomenon reshapes our understanding of galaxy evolution and the distribution of black holes throughout the cosmos. In addition to gravitational waves, astronomers strive to capture electromagnetic counterparts to these mergers, flashes of light or bursts of radiation emitted in the aftermath when gas around merging black holes ignites. Such multi-messenger astronomy enables richer insights into the merger environment and the physics governing accretion and jet formation. Recent breakthroughs include the first-ever imaging of two massive black holes orbiting each other in a binary system. These cosmic giants, vastly different in mass, dance at close quarters separated by light months, their interactions visible through precise radio observations. Their periodic orbits and emissions provide a natural laboratory to study the dynamics leading to black hole mergers, addressing long-standing puzzles about how such massive pairs form and evolve amidst the cosmic landscape. This discovery connects with broader galaxy merger dynamics. When galaxies collide, their central black holes are brought together through complex interactions, eventually forming binaries that spiral inward via gravitational wave emission. Understanding how these pairs overcome obstacles like the final parsec problem involves studying their interactions with surrounding gas and stars, often revolving around concepts like circumbinary disks that facilitate angular momentum loss. The technical challenges faced by gravitational wave detectors are immense. Measuring space-time distortions smaller than a proton's width requires laser stabilization, vibration isolation, and unprecedented noise reduction. Despite the challenges, a global network of observatories collaborates seamlessly to detect and analyze these waves, pushing the boundaries of precision measurement. The implications of these discoveries extend beyond astrophysics. The technology born from gravitational wave astronomy influences fields ranging from quantum optics to data processing. It exemplifies how curiosity-driven research fosters innovation, impacting multiple domains. Looking forward, space-based gravitational wave observatories will open new frequency windows to observe supermassive black hole mergers and the slow dances of galactic cores. This next frontier promises to deepen our cosmic understanding, possibly revealing novel gravitational phenomena and shedding light on galaxy formation. As science advances, each detection refines our perspective and poses new questions. The seemingly silent universe is rich with tales waiting to be told, and black hole mergers are among the most dramatic chapters. Looking up at the night sky, we see single points of light, each representing a star or galaxy. But hidden within those distant galaxies are cosmic dramas playing out on scales that challenge our imagination. Recently, astronomers achieved something that seemed impossible just years ago. They captured the first direct image of two supermassive black holes locked in a gravitational dance around each other. These aren't just theoretical objects or computer simulations. They're real, they're orbiting, and we can finally see them both. The discovery came from combining observations from multiple radio telescopes across the globe, working together to create a virtual instrument with resolution sharp enough to distinguish two distinct black holes separated by mere light months. The primary black hole in this system weighs approximately 18 billion times the mass of our Sun, making it one of the most massive black holes ever measured. Its companion, though smaller, still tips the scales at around 150 million solar masses. To put this in perspective, that smaller black hole alone outweighs every star within hundreds of light years of Earth combined. These titans orbit each other roughly once every 12 years, bound together by gravity in a cosmic waltz that has likely continued for millions of years. Each black hole sits at the center of its own accretion disk, a swirling vortex of superheated gas and dust spiraling inward. The disks glow brilliantly in radio wavelengths, allowing astronomers to pinpoint the exact location of each black hole. Between the two black holes stretches a bridge of material, gas pulled and twisted by the competing gravitational fields, heated to millions of degrees as it's squeezed and stretched. The system reveals itself through periodic variations in brightness. As the black holes swing past each other, they compress the gas between them, heating it and causing flares of radiation. These flares follow a predictable pattern, repeating with each orbit, providing a cosmic clock that astronomers can use to measure the orbital period with remarkable precision. The observations show that the black holes are slowly spiraling inward, losing energy through gravitational wave emission and interactions with surrounding gas. Based on current measurements, they're expected to merge in roughly 10,000 years, a blink of an eye in cosmic terms, but far too long for any human observer to witness directly. This binary system didn't form by accident. It's the product of a galaxy merger, a collision between two massive galaxies that occurred hundreds of millions of years ago. When galaxies collide, their stars rarely actually hit each other because space between stars is so vast. But the galaxy's central black holes, each weighing billions of solar masses, inevitably sink toward the center of the merged galaxy through a process called dynamical friction. As the black holes plow through the sea of stars and gas, gravitational interactions transfer momentum, causing the black holes to lose orbital energy and spiral inward. This process works efficiently at first. When the black holes are separated by thousands of light years, interactions with stars and gas quickly drain their orbital energy. But as they get closer, Within a few light years of each other, the process becomes much less efficient. This is known as the final parsec problem, and it puzzled astronomers for decades. At these separations, most stars and gas have already been scattered or consumed, leaving little material to interact with the binary and remove energy. Some scientists worried that black hole binaries might stall at this separation, never quite making it to the final merger. The discovery of this tight binary system, along with theoretical advances, suggests that the final parsec problem might solve itself in gas-rich environments. The two black holes are surrounded by a circumbinary disk, a massive reservoir of gas and dust, orbiting both black holes. Gravitational torques between the binary and the disk can continue extracting energy and angular momentum from the orbit, driving the black holes together, even at small separations. Computer simulations show that under the right conditions, circumbinary disks can efficiently shepherd black holes to merger, overcoming the final parsec problem. The interactions between the binary and its disk create fascinating dynamics. The gravitational pull of the black holes carves a gap in the inner disk, clearing out a region around the binary. Gas from the outer disk flows inward, crossing through resonances where the orbital periods match specific ratios with the binary period. At these resonances, gravitational torques are strongest, and gas can transfer angular momentum most efficiently. Some gas streams cross the gap, feeding the individual accretion disks around each black hole, while tidal forces and orbital motion create spiral density waves that propagate through the disk. These waves heat the gas, causing it to radiate energy and lose angular momentum. The waves also modulate the disk's brightness, creating additional periodic signals that astronomers can observe. By studying these modulations, scientists can map the structure of the disk and understand how gas flows in the complex gravitational environment around binary black holes. This information is crucial for predicting the timeline to merger and understanding how supermassive black holes grow through cosmic history. The existence of such binary systems has profound implications for gravitational wave astronomy. When these supermassive black holes finally merge, they'll produce gravitational waves at frequencies far lower than what current ground-based detectors can observe. These waves will be detectable by future space-based observatories, which will float in orbits around the Sun, using laser beams millions of kilometers long to measure space-time distortions. The merger of supermassive black holes will be among the loudest events these detectors will hear, providing unprecedented tests of general relativity in extreme gravity and allowing precise measurements of black hole masses, spins, and orbital parameters. Observing supermassive black hole binaries in their late stages also helps calibrate models of galaxy evolution. The merger rate of supermassive black holes depends on how often galaxies collide and how efficiently black holes can overcome the final parsec problem. By counting how many tight binaries exist and measuring their orbital decay rates, astronomers can constrain these processes and predict how many mergers should be occurring across the universe at any given time. These predictions can then be tested against future gravitational wave detections, closing the loop between electromagnetic and gravitational wave observations. The jets launched by these black holes add another layer of complexity. Both black holes appear to be launching relativistic jets, narrow beams of plasma, accelerated to nearly the speed of light. The jets interact with each other and with the circumbinary disk, creating shock waves and additional heating. As the binary evolves and the black holes spiral closer, the jets might wobble or even shut off temporarily if the accretion rate drops. Observations of jet variability in binary systems provide clues about the connection between orbital dynamics and jet launching mechanisms. Some binary black hole systems show evidence of precession, where the orbital plane itself wobbles over time due to relativistic effects and interactions with the disk. This precession can cause periodic changes in how we observe the system from Earth. As different parts of the orbit come into view, precessing binaries are particularly interesting because they provide additional ways to measure the black hole masses and spins, and they test aspects of general relativity that are difficult to probe in other ways. The discovery of this binary system also raises questions about how common such objects are. If tight binaries are rare, it suggests that most black hole pairs either merge quickly or stall at larger separations. If they're common, it means the path to merger is efficient, and we should expect frequent supermassive black hole mergers across cosmic history. Current surveys are searching for more binary systems by looking for periodic variations in quasar-light curves, seeking pairs of black holes in the process of merging. So far, only a handful of candidates have been confirmed, but next-generation surveys will dramatically increase the sample size. Understanding binary black holes also informs our knowledge of how galaxies grow and evolve. Most massive galaxies have experienced multiple mergers throughout their history, and each merger brings together two supermassive black holes. The merged black hole continues to grow by accreting gas and possibly merging again in future galaxy collisions. Over billions of years, this process builds up the enormous black holes we observe in the centers of the most massive galaxies today, some weighing tens of billions of solar masses. The two black holes orbiting each other represent a snapshot in this grand cosmic cycle. They were once the central engines of separate galaxies, each governing the star formation and evolution of its host. When their galaxies collided, the black holes were brought together, and now they orbit as a binary, heading inexorably toward a final merger that will shake space-time itself. After they merge, the resulting black hole will continue influencing its galaxy, potentially launching powerful jets, heating the surrounding gas, and regulating how the galaxy forms new stars for billions of years to come. This discovery bridges multiple frontiers in astrophysics. It connects galaxy evolution to black hole physics, electromagnetic observations to gravitational wave predictions, and theoretical models to observational reality. It demonstrates that the universe's most extreme objects are not isolated curiosities but central players in the cosmic drama of structure formation and evolution. Every new observation of binary black holes refines our understanding and brings us closer to a complete picture of how the universe assembled itself over cosmic time. The image itself represents a triumph of technology and international collaboration. Radio observatories spanning multiple continents synchronize their observations, recording vast amounts of data that had to be carefully calibrated and combined. The resulting image shows two bright spots, each representing a black hole surrounded by glowing gas, separated by a dark gap where the binary's gravity has cleared out material. Around them lies the broader disk, its structure shaped by the orbital dance of the black holes. In recent weeks, astronomers working with the Event Horizon Telescope have uncovered tantalizing hints that black holes may serve not only as cosmic vacuum cleaners, but also as powerful detectors of dark matter, the invisible substance that makes up most of the universe's mass. The key lies in subtle distortions of magnetic fields and light polarization in the swirling maelstrom of gas orbiting a supermassive black hole. By analyzing these distortions, researchers have begun to map the distribution and properties of dark matter halos in galactic centers, revealing new ways to probe the dark sector of the cosmos. The foundation of this approach dates back to the discovery that the accretion disk around a black hole emits synchrotron radiation as charged particles spiral along magnetic field lines. This radiation becomes polarized in a pattern that directly reflects the geometry and strength of the magnetic fields in the emitting region. When the Event Horizon Telescope captured its first polarized image of M87E, it showed a coherent polarization pattern tracing out magnetic lines at the edge of the black hole's shadow. Researchers compared the observed pattern to simulations that include only ordinary matter, hot plasma, obeying magnetohydrodynamics, and found small but significant discrepancies. These discrepancies hinted at the presence of additional gravitational influence not accounted for by the visible material. Dark matter, while not interacting electromagnetically, exerts gravity that can subtly reshape the accretion flow. In particular, a dense dark matter halo surrounding a supermassive black hole would deepen the gravitational potential well, altering the orbits of plasma clumps and the twist of magnetic field lines. The result is a shifted polarization map, with certain regions appearing brighter or more ordered than expected, and characteristic asymmetries emerging in the ring of light. To extract the dark matter signature, scientists developed a new computational pipeline. First, they generated a library of simulated polarization images for a range of dark matter densities, assuming different spatial distributions, from chord halos to cuspy profiles predicted by cold dark matter theories. Next, they ran general relativistic magnetohydrodynamic simulations of accretion disks orbiting black holes embedded in each halo model. These simulations included ray tracing codes to predict the systematic polarization patterns an Earth-based observer would detect at millimeter wavelengths. By comparing the library of synthetic images with the actual EHT polarization data for M87C, researchers employed a Bayesian inference scheme to determine which dark matter profiles best matched observations. The result was a surprisingly tight constraint on the dark matter density within a few tens of gravitational radii of the black hole. While the uncertainties remain significant, the favored models indicate a dark matter density several thousand times higher than in the solar neighborhood, consistent with expectations for a dense galactic core. This breakthrough has opened several new avenues of research. One involves studying other supermassive black holes with strong polarized emission, such as those in nearby radio galaxies and quasars. By gathering a sample of polarization maps for different systems, astronomers can begin to chart how dark matter halos vary with galaxy type, black hole mass, and environment. Such a survey promises to complement stellar dynamics and gravitational lensing studies, extending dark matter mapping into the innermost regions of galaxies where traditional tracers cannot reach. Another promising direction comes from the physics of ultralight axion-like particles, a leading dark matter candidate. In the presence of a spinning black hole, axions can form clouds via a process called superradiance, extracting rotational energy from the black hole and amplifying the axion field. These gravitational atoms emit nearly monochromatic gravitational waves as the axions transition between energy levels. Simultaneously, the axion cloud interacts with magnetic fields and plasma, producing periodic modulations of the polarization signal at frequencies determined by the axion mass. Last month, teams using the EHT and the Very Large Array reported hints of such periodic polarization swings in a different black hole system. Although the evidence is tentative and requires further confirmation, the pattern matches predictions for axions with masses around 10 to the -17th electron volts. If confirmed, this would represent the first non-gravitational detection of dark matter, opening a direct window into particle physics using astrophysical observations. Meanwhile, theorists have refined the models of dark matter clustering around black holes, combining n-body simulations of galaxy formation with general relativity. These efforts show that dark matter can pile up near the innermost stable circular orbit, creating a mini halo or spike whose density rises steeply inward. Such spikes enhance the gravitational lensing of background stars crossing near the black hole, leading to detectable astrometric shifts. Future high-precision infrared interferometers planned for the next decade may trace these shifts, providing an independent probe of dark matter distribution. The synergy between polarization imaging, gravitational wave searches for axion clouds, and astrometric lensing measurements forms a multi-pronged strategy for dark matter detection. Each method probes different interactions. Electromagnetic polarization reveals the influence of dark matter gravity on plasma. Gravitational waves target dark matter particle couplings to space-time, and lensing astrometry measures pure gravitational deflections. Together, they promise to transform black holes into cosmic laboratories for fundamental physics. On the observational front, engineers are working to enhance the polarization capabilities of current telescopes. Upgrades to the EHT network will add new stations in the southern hemisphere, improving image fidelity and time resolution. This will allow scientists to track temporal changes in polarization patterns, separating dynamic plasma events from the static influence of dark matter. The goal is to produce time-resolved polarization movies that reveal how magnetic fields evolve around black holes, while isolating the persistent signature imprinted by dark matter. Parallel to ground-based efforts, proposals are advancing for a space-based millimeter-wave interferometer. Free from atmospheric absorption, and equipped with larger baselines, such an observatory could image black holes at unprecedented resolution and sensitivity. By capturing polarization patterns in dozens of systems, it would enable a statistical survey of dark matter properties across cosmic time, tracking how halos grow and interact with black holes during galaxy evolution. The implications for cosmology are profound. Dark matter mapping has traditionally relied on observations of large-scale structure, galaxy rotation curves, and gravitational lensing of distant quasars. These methods probe scales from kiloparsecs to gigaparsecs, but leave the inner parsecs of galaxies largely uncharted. Black hole polarization studies fill this gap, extending our measurements into regions of extreme gravity where dark matter physics may differ, potentially revealing new particle properties or signaling deviations from cold dark matter models. As these techniques mature, we anticipate a rich harvest of data that challenges or confirms our understanding of dark matter. Gravitational wave detectors will directly observe mergers of black holes embedded in dark matter spikes, measuring the waveforms modified by the surrounding mass distribution. These detections will cross-validate polarization-based inferences, weaving a consistent narrative of dark matter behavior from event horizons to cosmic web filaments. To capitalize on these opportunities, the astrophysics community is building new interdisciplinary collaborations, bringing together experts in plasma physics, general relativity, computational cosmology, and particle theory. Workshops over the past year have focused on standardizing simulation frameworks and data analysis pipelines, ensuring that polarization maps and gravitational wave signals can be jointly interpreted in a unified context. Despite the excitement, significant challenges remain. Polarization measurements are sensitive to calibration uncertainties, atmospheric effects, and instrumentation biases. Disentangling dark matter signatures from ordinary plasma physics requires robust modeling of turbulence, magnetic dynamo processes, and relativistic jet interactions. Simulations must capture a vast dynamic range, from the event horizon to the outer disk, while including the gravitational contribution of dark matter halos. Computational resources and algorithmic innovations are essential to meet these demands. On the theoretical side, uncertainties in dark matter particle properties, mass, self-interactions, and couplings to standard matter translate into uncertainties in predicted halo profiles and axion cloud behavior. Laboratory experiments searching for axions, sterile neutrinos, and WIMPs continue to refine parameter spaces, but astrophysical observations offer a complementary path, probing interactions that would be impossible to recreate on Earth. Coordination between laboratory and astronomical efforts will be vital to converge on a consistent picture of dark matter. The promise of detecting dark matter through black hole astrophysics hinges on perseverance and innovation. Each incremental improvement in telescope sensitivity, simulation fidelity, and theoretical modeling sharpens our view of the dark sector. The testing whether the initial hints from M87T polarization unlock a new frontier or require rethinking our assumptions drives progress across disciplines, pushing technology and theory in tandem. Through polarization, through gravitational whisperings of axion clouds, and through astrometric lensing, these cosmic titans illuminate the darkness, turning the enigmas of the dark universe into tangible scientific targets that can finally be measured, mapped, and understood with the precision modern astronomy demands. Albert Einstein spent years wrestling with the equations of general relativity, seeking to understand how mass and energy warp the fabric of space-time. His theory made bold predictions about the universe, many of which seemed impossible to test at the time. Black holes represented one of the most extreme consequences of his mathematics, objects so dense that space-time curves back on itself, creating a boundary from which nothing can escape. For decades, these remained mathematical curiosities, solutions to equations rather than physical realities. Stephen Hawking entered the story in the 1970s, bringing quantum mechanics into the conversation. His revelation that black holes emit radiation shocked the physics community. If black holes radiate, they lose mass. If they lose mass, they eventually evaporate. This raised profound questions about what happens to the information contained in objects that fall into a black hole. Quantum mechanics insists that information cannot be destroyed, yet Hawking's calculations suggested it disappears when a black hole evaporates completely. The information paradox was born, and it remains one of the deepest puzzles in theoretical physics. Recent observations have put both Einstein and Hawking to the test in ways that would have seemed like science fiction even 20 years ago. The detection of gravitational waves from merging black holes provided the first direct confirmation that these objects exist and behave exactly as general relativity predicts. The waveforms detected by LIGO and Virgo match Einstein's predictions with remarkable precision, confirming that space-time really does ripple when massive objects accelerate, and that these ripples travel at the speed of light. The most stringent test came from analyzing the ring-down phase after two black holes merge. When the event horizons coalesce, the resulting black hole is momentarily distorted, like a struck bell. It vibrates, emitting gravitational waves at characteristic frequencies determined solely by its mass and spin. These quasi-normal modes are a fingerprint of the black hole, predicted precisely by general relativity. Any deviation would signal new physics, modifications to gravity, extra dimensions, or exotic matter. The observations matched theory to within a fraction of a percent. Hawking's area theorem received similar validation. This theorem states that the total area of black hole event horizons can never decrease in any physical process. During a merger, even though mass energy is radiated away as gravitational waves, the area of the final black hole's horizon must exceed the combined areas of the two original horizons. Measurements from the gravitational wave signals confirmed this prediction. The area increased exactly as Hawking predicted, providing strong evidence that his semi-classical approach to black hole thermodynamics captures real physical behavior. The connection between black hole area and entropy runs deep. Jacob Bekenstein proposed in the early 70s that black holes have entropy proportional to their horizon area. Hawking's discovery of black hole radiation cemented this connection, showing that black holes have a temperature inversely proportional to their mass. This suggests that black holes are thermodynamic objects, obeying laws analogous to those governing heat engines and refrigerators. The entropy of a black hole represents the number of quantum states consistent with its macroscopic properties, mass, spin, and charge. This leads directly to the information paradox. In classical general relativity, anything that falls into a black hole is lost forever, erased from the universe. But quantum mechanics forbids the destruction of information. If you burn a book, the information it contained is scrambled into smoke, heat, and ashes, but in principle, it could be reconstructed by tracking every particle. A black hole seems to violate this principle. Objects fall in, carrying information, and that information appears to vanish when the black hole evaporates via Hawking radiation, which is perfectly thermal and contains no trace of what fell in. Physicists have proposed various solutions to this paradox over the decades. One idea involves the holographic principle, which suggests that all the information about a volume of space can be encoded on its boundary. Applied to black holes, this means the information about everything that falls in gets scrambled and encoded on the event horizon, then slowly released through subtle correlations in the Hawking radiation. Retrieving the information would require collecting all the radiation emitted over the black hole's lifetime and performing impossibly complex measurements, but in principle, the information survives. Another approach involves quantum entanglement between the infalling matter and the outgoing radiation. As particles fall toward the horizon, they become entangled with particles near the horizon. When Hawking radiation escapes, it carries away part of this entanglement, gradually transferring the information outward. Recent theoretical work using ideas from quantum information theory has shown that this transfer can preserve information, resolving the paradox without violating any fundamental principles. The concept of black hole complementarity takes this further. From the perspective of an outside observer, nothing ever crosses the event horizon. It appears to spread out and thermalize on the horizon's surface, eventually re-emitted as Hawking radiation. From the perspective of an infalling observer, the crossing is smooth and uneventful, with no sign of a barrier. Both descriptions are valid in their respective reference frames, and information is preserved in the outside observer's frame. This duality mirrors similar ideas in quantum mechanics, where different observers can have different but equally valid descriptions of the same physical system. Testing these ideas observationally is extraordinarily difficult. Hawking radiation from astrophysical black holes is far too weak to detect. A solar mass black hole has a temperature of about 1/millionth of a degree above absolute zero, far colder than the cosmic microwave background. For supermassive black holes, the temperature is even lower. Detecting Hawking radiation directly would require waiting for black holes to shrink to much smaller sizes, a process that takes unimaginably long times. However, physicists have found ways to test related concepts using analog systems. Sonic black holes created in flowing fluids, optical black holes in nonlinear media, and cold atom systems can mimic aspects of black hole physics, including analogs of Hawking radiation. These experiments have confirmed some predictions of semi-classical gravity, lending support to the theoretical framework even if direct detection of real Hawking radiation remains out of reach. The Event Horizon Telescope observations of M87 CAM provide another kind of test. The size and shape of the black hole's shadow depend on the space-time geometry near the event horizon, which is determined by general relativity. The shadow's diameter is about 2.5 times the Schwarzschild radius, consistent with predictions. Any deviation would indicate modifications to Einstein's equations or the presence of exotic matter near the horizon. The observations show no such deviations, confirming general relativity in the strong field regime. The changing magnetic fields around M87 add another dimension to these tests. If general relativity breaks down near the event horizon, the dynamics of the accretion disk and magnetic fields might behave differently than simulations predict. The rapid flip in magnetic field orientation challenges our models but doesn't contradict general relativity. It suggests the plasma dynamics are more complex than we thought, involving instabilities and reconnection events that current simulations struggle to capture. Improving these simulations will sharpen future tests of fundamental physics. Looking forward, gravitational wave astronomy will continue probing general relativity with increasing precision. As detectors become more sensitive, they'll observe smaller black holes at greater distances, capturing waveforms with higher fidelity. Space-based detectors will access lower frequencies, observing supermassive black hole mergers and providing tests in different regimes. Each new detection either confirms Einstein's theory or hints at deviations that could point toward quantum gravity. The merger of neutron stars with black holes offers another testing ground. Neutron stars have complex internal structures and equations of state that affect the gravitational waves they emit during a merger. By comparing observations with predictions, scientists can probe the behavior of matter at nuclear densities and test whether general relativity accurately describes the merger dynamics. Recent detections of neutron star black hole mergers have begun this program, with more events expected as detectors improve. Quantum gravity remains the holy grail of theoretical physics, a theory that unifies general relativity and quantum mechanics into a consistent framework. Black holes are where these two pillars of modern physics collide most dramatically. Near the singularity, quantum effects and strong gravity both matter, and neither theory alone suffices. String theory, loop quantum gravity, and other approaches attempt to resolve this tension, predicting modifications to black hole interiors or even replacing singularities with smooth quantum structures. One intriguing possibility is that black hole singularities might not exist at all. Quantum effects could halt the collapse before infinite density is reached, creating a black hole firewall or some other exotic structure. Observations cannot peer inside event horizons to test these ideas directly, but they can look for indirect signatures in the behavior of matter near the horizon or in the properties of Hawking radiation, if it ever becomes detectable. The interplay between theory and observation drives progress. Einstein and Hawking provided the theoretical foundation, predicting phenomena that seemed beyond reach. Modern observatories have now confirmed many of those predictions, validating the theories in extreme conditions. Yet mysteries remain. The information paradox still lacks a universally accepted solution. The nature of singularities remains speculative. Quantum gravity remains incomplete. Each answer raises new questions, pushing the boundaries of knowledge ever outward. Black holes continue to serve as cosmic laboratories, testing the laws of physics in regimes we can never recreate on Earth, revealing truths about the universe that challenge our deepest assumptions about reality itself. The universe contains black holes of truly staggering proportions, objects so massive they challenge our ability to comprehend scale. At the extreme end sits TON 618, a quasar powered by what may be the most massive black hole ever measured. Observations suggest this monster weighs approximately 66 billion times the mass of our Sun. To put this in perspective, if you replaced our Sun with TON 618, its event horizon would extend far beyond the orbit of Neptune, swallowing our entire solar system and reaching outward for hundreds of astronomical units. TON 618 resides more than 10 billion light-years away, meaning we see it as it existed when the universe was less than a quarter of its current age. At that early epoch, this black hole was already fully grown, shining as one of the brightest quasars in the sky. The accretion disk surrounding it converts in falling matter into radiation with such efficiency that TON 6018 outshines entire galaxy clusters. The luminosity is almost incomprehensible, equivalent to 400 trillion times the Sun's output. Material spiraling into this behemoth heats to millions of degrees, radiating across the electromagnetic spectrum from radio waves to X-rays. How such an enormous black hole formed so early in cosmic history remains a puzzle. Standard models of black hole growth suggest they start from stellar mass seeds and grow by accreting gas and merging with other black holes over billions of years. But TON 618 appears to have reached its colossal size in less than a billion years after the Big Bang. Either it started from an unusually massive seed, perhaps a direct collapse black hole formed from a primordial gas cloud, or it accreted matter at rates far exceeding what we thought possible. Some theories propose that supermassive black holes in the early universe fed from dense streams of cold gas funneled along cosmic web filaments, allowing rapid growth that would be impossible in the modern universe. Phoenix A presents another extreme case. The black hole at the center of the Phoenix cluster weighs around 100 billion solar masses according to some estimates, though measurements vary and this figure remains uncertain. What makes Phoenix A remarkable is the power of its jets. Radio observations reveal enormous lobes of plasma extending millions of light-years from the galactic center, inflated by jets that have been active for hundreds of millions of years. The energy required to create these structures is staggering, suggesting that Phoenix A has been feeding voraciously and converting that mass into kinetic energy with extraordinary efficiency. The jets from Phoenix A affect the entire galaxy cluster, heating the intergalactic gas and preventing it from cooling and forming new stars. This feedback mechanism regulates star formation on the largest scales, demonstrating how supermassive black holes influence their environments far beyond the immediate vicinity of the event horizon. The radio lobes act like cosmic cavities, displacing hot gas and creating shock waves that propagate through the cluster. These shocks compress and heat the gas, maintaining temperatures of tens of millions of degrees across volumes spanning millions of cubic light-years. Closer to home, at the center of our own Milky Way galaxy, sits Sagittarius A star, a relatively modest supermassive black hole weighing about 4 million solar masses. While tiny compared to TON 618 or Phoenix A, Sagittarius A star is by far the most studied black hole in the universe because of its proximity. Only 26,000 light-years away, astronomers have tracked stars orbiting this black hole for decades, watching them complete elliptical orbits that bring them within light hours of the event horizon, at speeds approaching 3% of light speed. One particular star, designated S2, has an orbital period of just 16 years. At its closest approach, it experiences gravitational fields strong enough to test general relativity in ways impossible anywhere else in the galaxy. Observations of S2's orbit have confirmed relativistic effects, including gravitational redshift, where light climbing out of the black hole's gravity loses energy and shifts toward longer wavelengths, and orbital precession, where the orbit itself rotates over time due to space-time curvature. Sagittarius A star is remarkably quiet for a supermassive black hole. Unlike quasars and active galactic nuclei that blaze across cosmic distances, our galactic center emits relatively little radiation. The black hole accretes matter at a trickle, far below its maximum possible rate. Occasionally it flares, briefly brightening in X-rays and infrared as a clump of gas or perhaps a small asteroid falls in, but most of the time it sits quiescent, a sleeping giant at the heart of the galaxy. The Event Horizon Telescope collaboration has captured images of Sagittarius A star similar to those of M87 star, revealing the characteristic shadow surrounded by a ring of emission from the accretion disk. The imaging was more challenging because Sagittarius A star varies on much shorter timescales. The smaller mass means material orbits faster, completing circuits around the black hole in minutes rather than days. During the hours-long observations needed to synthesize an image, the accretion disk changes, blurring the final result. Scientists develop new techniques to account for this variability, effectively taking snapshots fast enough to freeze the motion. Between these extremes lie countless other supermassive black holes spanning a wide range of masses. The relationship between black hole mass and galaxy properties reveals a tight correlation. More massive galaxies harbor more massive black holes, with the black hole typically weighing about 1/5 of the galaxy's bulge mass. This correlation suggests that black holes and galaxies grow together, influencing each other through feedback processes that regulate star formation and gas flows. Some black holes punch above their weight, accreting at or near the Eddington limit, the maximum rate at which radiation pressure from the accretion disk balances the inward pull of gravity. These objects shine as quasars and ultraluminous X-ray sources, visible across cosmic distances. Others, like Sagittarius A star, accrete far below this limit, remaining dim and difficult to detect except through their gravitational influence. Intermediate mass black holes occupy the gap between stellar mass and supermassive black holes, weighing hundreds to hundreds of thousands of solar masses. These objects have been elusive, with only a handful of candidates confirmed. They might form in dense star clusters through runaway collisions, or they could be the seeds from which supermassive black holes grow. Recent gravitational wave detections have hinted at black holes in this mass range, suggesting they may be more common than previously thought. The largest stellar mass black holes result from the collapse of the most massive stars, those exceeding perhaps 50 or 100 solar masses. These stars burn through their nuclear fuel in just a few million years, ending their lives in spectacular supernova explosions or direct collapse. The resulting black holes can weigh dozens of solar masses, occasionally reaching nearly 100 solar masses in rare cases. These represent the upper limit of what stellar evolution can produce through normal channels. Primordial black holes, if they exist, could span an enormous range of masses. These hypothetical objects would have formed in the early universe from density fluctuations, not from stellar collapse. They could be as light as a fraction of a gram or as massive as millions of suns. Searches for primordial black holes through gravitational lensing and other techniques have placed constraints on their abundance, but they remain a possible component of dark matter in certain mass ranges. The comparison between these black holes reveals the incredible diversity of these objects, from stellar corpses barely massive enough to overcome neutron degeneracy pressure to monsters weighing billions of suns. Black holes span more than 10 orders of magnitude in mass. Their environments range from isolated wanderers drifting through intergalactic space to the chaotic centers of active galaxies, where material spirals inward at near-light speed. Their ages span from the earliest epochs of the universe to black holes forming this very day from dying stars. Visualizing these extremes challenges the imagination. If you could place TON 618 at the center of our solar system, its event horizon would extend past Pluto's orbit. The jets from Phoenix A stretch across distances that would span from our location to the nearest galaxy clusters. Yet Sagittarius A star, massive by stellar standards, would fit comfortably within Mercury's orbit. The range of scales involved mirrors the diversity of phenomena black holes produce, from the gentle tug on stars orbiting Sagittarius A star to the universe-shaking mergers detected by gravitational wave observatories. Each of these objects teaches us something different about black hole physics and cosmic evolution. The existence of ultramassive black holes like TON 618 in the early universe constrains models of structure formation and black hole seeding. The powerful jets from Phoenix A demonstrate how black holes regulate their environments on cluster scales. Sagittarius A star provides a laboratory for testing general relativity and studying accretion physics in exquisite detail. Intermediate mass black holes, if we can find more of them, will fill a crucial gap in our understanding of how black holes form and grow. The search for even larger black holes continues. As telescopes probe deeper into space and further back in time, they may discover even more massive objects, pushing the boundaries of what we thought possible. Each discovery refines our understanding of how these cosmic giants form, grow, and shape the universe around them, revealing the intricate connections between black holes and the cosmic structures they inhabit. Crossing the event horizon of a black hole represents the ultimate one-way journey, a point of no return where even light cannot escape. What happens beyond that boundary has fascinated and puzzled physicists for decades. The mathematics tells us one story, but the reality might be stranger than any equation can capture. To understand what lies inside a black hole, we need to follow the path of an unfortunate traveler falling toward the event horizon and beyond. From a safe distance, watching someone fall into a black hole reveals something extraordinary about time itself. As your companion approaches the horizon, they appear to slow down. Their movements become sluggish, their clock runs slower compared to yours, and the light from their body shifts toward redder wavelengths as it climbs out of the deepening gravitational well. Eventually, they seem to freeze at the horizon's edge, their image growing dimmer and redder until they fade from view entirely. From your external perspective, they never actually cross the horizon. They remain suspended there forever, asymptotically approaching but never quite reaching that fatal boundary. But from the perspective of the falling traveler, the experience is entirely different. They cross the horizon in finite time, experiencing nothing particularly unusual at that moment. There's no barrier, no wall, no sensation marking the passage across this cosmic point of no return. Looking outward, they would see the universe above them appear to speed up and brighten, compressed by relativistic effects into a shrinking circle of light. Looking ahead toward the center, they would see only darkness, the inevitable singularity that awaits. And here's the crucial point. Once across the horizon, all paths lead inward. The singularity is no longer a place in space, but a moment in time, an unavoidable future, rather than a destination you might avoid. As the traveler continues falling, tidal forces begin to make themselves known. These forces arise because gravity's strength depends on distance. The side of your body closer to the black hole experiences stronger gravitational pull than the side farther away. For a supermassive black hole like M87 star, these tidal forces remain manageable even at the horizon because the horizon is so large and the curvature relatively gentle. An astronaut could cross the event horizon without immediately being torn apart, surviving for precious seconds or perhaps minutes as they plunge toward the center. But for a stellar mass black hole, the story is different. The event horizon sits much closer to the center, where space-time curves more sharply. The tidal forces at the horizon would be immense, enough to pull atoms apart. Long before reaching the singularity, any object would be stretched vertically and compressed horizontally in a process physicists call spaghettification. Your body would be drawn into a thin stream of atoms, each experiencing slightly different gravitational acceleration, pulled inexorably inward along a trajectory that cannot be altered. The mathematics describing this journey comes from the Schwarzschild solution to Einstein's equations, which describes a non-rotating, electrically neutral black hole. But most black holes in nature rotate, some at tremendous speeds. Rotating black holes are described by the Kerr solution, and their internal structure is far more complex. A rotating black hole drags space-time around with it in a process called frame dragging. Close to the black hole, this effect becomes so strong that nothing can remain stationary. Everything must rotate in the same direction as the black hole itself. Inside a rotating black hole, the event horizon is just the first boundary. Deeper within lies the ergosphere, a region where space-time is dragged so strongly that escape is still possible if you move fast enough in the right direction. The Penrose process allows energy to be extracted from a rotating black hole by dropping objects into the ergosphere and having them split, with one piece falling in and the other escaping with more energy than it started with. This mechanism could, in principle, power advanced civilizations, extracting rotational energy from black holes. Even deeper inside a Kerr black hole, the singularity takes a different form. Instead of a point, it becomes a ring, a circle of infinite density sitting at the equator of the black hole's rotation. The mathematics suggests that if you could somehow pass through this ring singularity without being destroyed, you might emerge into a region of space-time with strange properties. Negative gravitational fields, closed time-like curves that loop back on themselves, even pathways to other universes. These solutions are mathematically valid, but almost certainly physically unrealistic, representing places where general relativity breaks down and quantum effects must become important. The singularity itself represents the ultimate boundary of our understanding. General relativity predicts that all the mass of the black hole gets compressed to infinite density in zero volume, a point where space-time curvature becomes infinite, and the equations produce meaningless infinities. Most physicists believe this signals the breakdown of general relativity, rather than a description of physical reality. At the scales where quantum mechanics becomes important, the Planck length of about 10 to the minus 35 meters, space-time itself might become granular, quantized, no longer the smooth fabric described by Einstein. Various approaches to quantum gravity predict different fates for the singularity. String theory suggests that stringy effects might smear out the singularity, replacing the point of infinite density with a small but finite region where strings interact in complex ways. Loop quantum gravity proposes that quantum geometry could halt the collapse before a singularity forms, potentially creating a bounce that connects the black hole to a white hole or another region of space-time. These ideas remain speculative, awaiting a complete theory of quantum gravity to make definite predictions. White holes represent the time-reversed version of black holes, regions of space-time from which matter and light can only exit, never enter. While mathematically valid solutions to Einstein's equations, white holes have never been observed and probably don't exist in nature. If they did, they would be spectacularly unstable, eventually collapsing or transforming into black holes. The asymmetry between black holes and white holes reflects the thermodynamic arrow of time, the increase of entropy that distinguishes past from future. Wormholes, or Einstein-Rosen bridges, represent another exotic possibility. These hypothetical structures connect two distant regions of space-time through a shortcut, a tunnel through the fabric of space itself. The interior of a black hole might connect to another point in space, allowing travel between locations without traversing the distance between them. However, wormholes face severe problems. The simplest wormhole solutions collapse too quickly for anything to pass through. Keeping a wormhole open would require exotic matter with negative energy density, something that might be possible through quantum effects, but has never been created in meaningful quantities. Even if traversable wormholes could exist, using them presents paradoxes. A wormhole connecting two points in space could be manipulated to connect different points in time, creating the possibility of closed time-like curves and time travel paradoxes. An object could potentially travel back in time and prevent its own creation, violating causality. Various resolution mechanisms have been proposed, from self-consistency constraints that only allow timelines without paradoxes to quantum effects that prevent the formation of time machines, but these remain active areas of research. The information paradox adds another layer of mystery to black hole interiors. If information about everything that falls in really is preserved, as quantum mechanics demands, then the interior must somehow encode all that information in a way that eventually gets transmitted back out through Hawking radiation. The holographic principle suggests that this information is encoded on the event horizon itself, with the three-dimensional volume of the interior being redundant, a projection of the two-dimensional surface. This radical idea, inspired by black hole thermodynamics, has profound implications for how we understand space-time and the nature of reality itself. Recent theoretical work has explored the idea of black hole complementarity more deeply, suggesting that observers falling into a black hole and observers remaining outside experience incompatible but equally valid descriptions of reality. From outside, information never enters the black hole, but instead gets scrambled and encoded in the subtle correlations of Hawking radiation. From inside, the infalling observer experiences a smooth interior, with information genuinely crossing the horizon. Both descriptions are correct within their respective reference frames, much like how quantum mechanics allows different observers to have different but consistent descriptions of the same system. The firewall paradox highlighted tensions in this picture. If the Hawking radiation emitted early in a black hole's evaporation must be entangled with the radiation emitted later to preserve information, and if matter inside the black hole must also be entangled with the early radiation to maintain the smoothness of the horizon, then we face a contradiction. A quantum system cannot be maximally entangled with two different systems simultaneously. One proposed resolution involves a firewall of high-energy particles at the event horizon that destroys anything trying to cross, preserving the consistency of quantum mechanics at the cost of violating the smoothness predicted by general relativity. Alternative proposals avoid firewalls through various mechanisms. Some involve non-local effects that allow information to be transferred across large distances without violating relativity's prohibition on faster-than-light signaling. Others propose modifications to quantum mechanics itself, allowing states that appear impossible in standard quantum theory. The debate continues, with different camps favoring different resolutions, each with its own trade-offs and implications. Observationally, testing these ideas ideas remains nearly impossible. We cannot peer inside a black hole's event horizon to see whether a firewall exists or whether the interior is smooth. We cannot detect Hawking radiation from astrophysical black holes or measure the subtle correlations that would prove information is preserved. But indirect tests might be possible. Echoes in gravitational wave signals reflecting off quantum structure near the horizon could reveal deviations from classical general relativity. Persistent anomalies in accretion disk behavior might hint at modified physics near the event horizon. These observations push the boundaries of what's detectable, requiring exquisite sensitivity and careful interpretation. The quest to understand black hole interiors drives progress in theoretical physics, forcing us to confront the limits of our current theories and imagine new frameworks that might resolve the contradictions. It's a journey into the unknown, guided by mathematics and constrained by observation, seeking to understand the most extreme environments the universe can produce. Every advance brings new questions, new puzzles, new opportunities to learn. The singularity at the heart of a black hole marks the boundary of our knowledge, a place where the maps end and terra incognita begins, waiting for future generations to explore. Imagine standing at the very edge of possibility, peering into an abyss where the rules governing reality begin to unravel. The event horizon of a black hole marks a boundary beyond which our ordinary experience of time and space ceases to function in recognizable ways. What awaits beyond that threshold has captivated minds for generations, blending rigorous mathematics with speculation about the nature of existence itself. The journey begins long before you reach the horizon. From thousands of kilometers away, gravitational forces start to make themselves felt, pulling you inexorably inward. The acceleration builds gradually at first, then with terrifying swiftness as you approach the point of no return. Light from the universe behind you appears compressed into a shrinking circle, blue shifted and brightened by relativistic effects. Ahead lies only darkness, the inevitable destination from which no signal can return. At the horizon itself, something profound happens to the structure of space-time. The roles of time and space exchange places in a sense that defies intuition. Just as we cannot avoid moving forward in time in ordinary space-time, once past the horizon, you cannot avoid moving inward toward the center. The singularity becomes not a place you might visit, but a moment in your future, as unavoidable as tomorrow. Every possible trajectory leads to the same destination, converging on that point where the mathematics of general relativity breaks down completely. For a supermassive black hole, spanning billions of solar masses, crossing the event horizon might be surprisingly gentle. The gravitational gradient across your body remains manageable because the horizon sits so far from the center. You could survive for minutes, perhaps longer, falling through a region of space-time that appears almost normal despite its exotic global properties. Instruments would show time dilation effects. Measurements of the external universe would appear strange, but locally the laws of physics operate much as they do anywhere else. But this grace period cannot last. Deeper inside, tidal forces grow inexorably stronger. These arise because gravity strengthens with proximity, creating a differential force across any extended object. Your feet, closer to the center than your head, experience stronger gravitational pull. Initially subtle, this differential becomes a stretching force, pulling you apart along the radial direction while simultaneously compressing you perpendicular to it. The process has earned the memorable name spaghettification, describing the fate of any object subjected to these extreme tidal stresses. For smaller black holes, the story turns violent much earlier. A stellar mass black hole concentrates its mass in a far smaller volume, creating steeper gradients in the gravitational field. The tidal forces at the event horizon of such an object would tear apart any structure held together by electromagnetic forces. Atoms themselves would be disrupted, their electron clouds stripped away, leaving only atomic nuclei streaming inward in a thin filament of matter. Long before reaching the central singularity, any recognizable structure would cease to exist, reduced to its elementary constituents and stretched across the curved geometry of the black hole interior. The mathematics describing these journeys comes from solutions to Einstein's field equations. The Schwarzschild solution, derived for a non-rotating, uncharged black hole, predicts a point singularity at the center where density and space-time curvature become infinite. But nature rarely produces perfectly spherical, non-rotating objects. Most black holes possess angular momentum, inherited from the rotation of the star that collapsed to form them, or acquired through asymmetric accretion of matter. Rotating black holes obey the Kerr solution, a more complex geometry that introduces new features. The ergosphere surrounds the event horizon, a region where spacetime is dragged along by the black hole's rotation so forcefully that remaining stationary becomes impossible. Everything within the ergosphere must rotate in the same direction as the black hole, though escape remains possible by moving fast enough against the frame dragging effect. Deeper still lies the event horizon proper, and beyond that the inner horizon and finally the ring singularity. Unlike the point singularity of a Schwarzschild black hole, a Kerr black hole contains a singularity with the topology of a ring positioned at the equator of the black hole's rotation. The mathematical solutions suggest extraordinary possibilities if matter could somehow pass through this ring without being destroyed. The geometry on the other side possesses strange properties, including regions of negative gravitational fields and closed time-like curves, paths through space-time that loop back to their own past. These features almost certainly represent places where general relativity breaks down rather than descriptions of physical reality, signaling the need for quantum gravity to understand what truly happens. The concept of the singularity itself represents the ultimate breakdown of our physical theories. General relativity predicts infinite density in zero volume, a statement that produces mathematical infinities whenever we attempt calculations. Most physicists interpret these infinities as a failure of the classical theory rather than a description of nature. At sufficiently small scales, the Planck length of roughly 10 to the minus 35 meters, quantum effects of spacetime itself should become important, potentially preventing the formation of true singularities. Various approaches to quantum gravity offer different visions of what might replace the classical singularity. String theory posits that fundamental constituents are not point particles, but tiny vibrating strings. At the scales where a classical singularity would form, these strings and their interactions might smear out the would-be singularity into a small but finite region, avoiding infinities through the extended nature of the fundamental objects. Loop quantum gravity takes a different approach, suggesting that space-time itself has a discrete structure at the smallest scales. This quantization of geometry could halt gravitational collapse before reaching infinite density, possibly creating a bounce that connects the black hole to a white hole or another region of spacetime. White holes represent time-reversed black holes, regions from which matter and radiation can only exit, never enter. While mathematically valid solutions to Einstein's equations, white holes have never been observed and likely don't exist in nature. They would be extraordinarily unstable, any small perturbation causing them to collapse or transform. The asymmetry between black holes and white holes reflects the thermodynamic arrow of time, the universal tendency toward increasing entropy that distinguishes past from future. Wormholes present another exotic possibility emerging from the mathematics of general relativity. An Einstein-Rosen bridge connects two distant regions of spacetime through a tunnel, a shortcut that bypasses the normal distance between locations. The interior structure of certain black hole solutions admits this possibility, raising the tantalizing prospect of using black holes for interstellar or even intergalactic travel. However, traversable wormholes face severe obstacles. The simplest solutions collapse too rapidly for anything to pass through. Keeping a wormhole open long enough to traverse requires exotic matter with negative energy density, something that quantum field theory permits in principle through effects like the Casimir force, but has never been produced in macroscopic quantities. Even if stable wormholes could exist, using them creates potential paradoxes. A wormhole connecting 2 points in space could be manipulated through relative motion to connect 2 points in time, creating closed time-like curves. An object could travel through the wormhole, emerge in its own past, and potentially interfere with events leading to its journey, creating a logical contradiction. Various mechanisms have been proposed to prevent such paradoxes, from consistency constraints that permit only self-consistent timelines to quantum effects that destroy any attempt to create a time machine, but these remain active research topics. The information paradox adds profound mystery to black hole interiors. Quantum mechanics insists that information cannot be destroyed, that complete knowledge of a quantum system at one time allows prediction of its state at any other time. But classical general relativity suggests that information falling into a black hole is lost forever, erased from the universe when the black hole eventually evaporates through Hawking radiation. Resolving this paradox has driven theoretical physics for decades. The holographic principle offers one resolution, suggesting that all information about a black hole's interior is encoded on its two-dimensional event horizon. The three-dimensional volume inside the black hole would be redundant, a projection of the information stored on the surface. This radical idea, inspired by black hole thermodynamics, has profound implications extending far beyond black holes to the fundamental nature of space-time and quantum gravity. Black hole complementarity proposes that different observers have incompatible but equally valid descriptions of what happens at the horizon. An observer falling through the horizon experiences a smooth interior, with information genuinely entering the black hole. An observer remaining outside sees information scramble and spread across the horizon, eventually re-emitted through subtle correlations in Hawking radiation. Both descriptions are correct within their respective reference frames, similar to how quantum mechanics allows different but consistent descriptions depending on which measurements are performed. The firewall paradox highlights tensions in this picture. If Hawking radiation must be entangled in specific ways to preserve information, and if matter inside must be entangled differently to maintain horizon smoothness, we face a contradiction since quantum systems cannot be maximally entangled with two partners simultaneously. Some resolutions propose a firewall of high-energy particles at the horizon that destroys anything attempting to cross, sacrificing smoothness to preserve information and quantum mechanics. Observationally testing these ideas remains extraordinarily challenging. We cannot see inside event horizons or detect Hawking radiation from astrophysical black holes, but indirect tests might be possible. Echoes in gravitational wave signals, reflecting off quantum structure near the horizon, could reveal deviations from classical predictions. Persistent anomalies in accretion disk behavior might hint at modified physics at the horizon. These observations push the boundaries of detectability, requiring exquisite sensitivity and careful interpretation to distinguish genuine quantum gravitational effects from complex classical plasma physics. The quest to understand black hole interiors drives theoretical physics forward, forcing confrontation with the limits of current theories and demanding new frameworks to resolve contradictions. The singularity at a black hole's heart marks the boundary of knowledge, where established physics gives way to speculation and where the next revolution in our understanding might emerge. Each advance brings new questions, new puzzles, new opportunities to probe deeper into the nature of reality itself, guided by mathematics and constrained by observation, seeking to understand the most extreme environments the universe produces. We started this journey with a puzzle that shook the foundations of black hole physics. The magnetic field surrounding M87 star, the supermassive black hole we first photographed in remarkable detail, had completely flipped its orientation in just a few years. Something thought to require millions of years happened in what amounts to an instant on cosmic scales. That discovery wasn't just an anomaly, it was a signal that black holes are far more dynamic, far more alive with change and complexity than we ever imagined. Throughout this exploration, we've seen how black holes challenge everything we thought we understood about the universe. They warp space-time itself into impossible geometries. They launch jets spanning millions of light years. They merge in collisions that shake the fabric of reality, sending gravitational waves across billions of light years. They may hold the key to detecting dark matter, testing the limits of Einstein's relativity, and probing the quantum nature of space-time at the smallest scales. Each discovery raises new questions, each answer opens new mysteries, and the pace of revelation continues to accelerate. The magnetic field flip at M87 star represents something profound about accretion physics. We now understand that the flows of gas around black holes are not steady, predictable streams, but chaotic, turbulent maelstroms where magnetic fields can build up, reconnect explosively, and reorganize on timescales we're only beginning to comprehend. The disk doesn't simply spiral inward smoothly. It transitions between states, chokes on its own magnetic pressure, then floods the black hole with matter in episodic bursts. These transitions affect everything from the brightness of the emission to the power of the jets, creating variability that astronomers have observed for decades but are only now beginning to explain. Understanding these dynamics requires better observations, more powerful simulations, and deeper theoretical insights. The Event Horizon Telescope collaboration continues to expand, adding new stations to its global network and upgrading existing facilities to observe at multiple frequencies simultaneously. The next generation of observations will capture not just single snapshots, but time-resolved movies showing how the emission patterns change hour by hour, day by day. These movies will reveal the dynamics of accretion in unprecedented detail, allowing scientists to track magnetic field evolution, identify reconnection events, and watch as material flows from the outer disk to the event horizon. Beyond Earth-based telescopes, ambitious plans are underway to extend black hole imaging into space. The Black Hole Explorer mission, currently in development, would place a satellite in Earth orbit equipped with a millimeter-wave telescope. Combined with ground-based stations, this space-based platform would create baselines spanning from Earth's surface to orbital altitude, dramatically improving resolution. With BHX, scientists could image smaller black holes at greater distances, study the immediate environment around the event horizon in exquisite detail, and potentially detect the predicted photon ring, a series of nested rings created by light orbiting the black hole multiple times before escaping. Gravitational wave astronomy stands on the threshold of revolutionary expansion. Current detectors like LIGO and Virgo have proven the concept, detecting dozens of black hole mergers and providing exquisite tests of general relativity. Next-generation ground-based detectors are already being planned, with sensitivity 10 times greater than current instruments. These observatories will detect mergers across the entire observable universe, revealing the populations of black holes at different cosmic epochs and tracking how these objects formed and evolved over billions of years. But the most transformative development will come from space. The Laser Interferometer Space Antenna, known as LISA, will launch within the next decade, placing 3 spacecraft in solar orbit separated by millions of kilometers. These spacecraft will track each other with laser precision, measuring gravitational waves at frequencies far below what ground-based detectors can access. LISA will hear the slow, majestic inspirals of supermassive black holes as they circle each other over years or decades before finally merging. It will detect compact binaries throughout the galaxy, map the distribution of stellar mass black holes, and potentially discover exotic objects we haven't even imagined yet. When LISA begins operations, it will revolutionize our understanding of supermassive black holes. We'll watch binary systems evolve in real time, measuring their masses, spins, and orbital parameters with extraordinary precision. We'll test general relativity in regimes that ground-based detectors cannot access. We'll probe the final parsec problem directly, observing how circumbinary disks and stellar interactions drive black holes together. And when electromagnetic telescopes detect flares or periodic variations associated with these binaries, we'll have true multi-messenger astronomy connecting gravitational and electromagnetic signals to understand the complete picture. The synergy between different observational techniques promises breakthroughs we can barely anticipate. Imagine detecting gravitational waves from a supermassive binary while simultaneously imaging the system with space-based telescopes, watching gas flow between the 2 black holes as they spiral inward. Imagine catching the electromagnetic flash when black holes merge within a dense gas cloud, seeing the shock waves propagate outward while gravitational waves carry information about the merger dynamics. These multi-messenger observations will transform black holes from abstract mathematical objects into tangible systems we can study with the full toolkit of modern astronomy. Theoretical physics continues to grapple with the deepest questions raised by black holes. The information paradox remains unresolved despite decades of effort. Multiple competing proposals each have their advocates, but no consensus has emerged. Future observations might provide crucial clues. If we could detect echoes in gravitational wave signals reflecting off quantum structure near the horizon, we'd have direct evidence for physics beyond classical general relativity. If we could observe deviations in the ring-down frequencies of merged black holes, we'd constrain models of quantum gravity. These observations push the boundaries of detectability, but improving sensitivity brings them closer to reality with each passing year. The quest to understand what happens inside black holes drives progress across multiple fronts. String theorists continue refining calculations of how strings behave in strong gravitational fields, seeking to replace the classical singularity with something physical. Loop quantum gravity researchers explore how quantized geometry might halt gravitational collapse before infinite density is reached. Numerical relativists develop ever more sophisticated simulations of merging black holes, pushing toward the moment of singularity formation where classical physics breaks down. Each approach offers pieces of the puzzle, and gradually a picture is emerging of space-time as fundamentally quantum, with classical smooth geometry being an approximation that fails at the smallest scales. Dark matter research using black holes is still in its infancy, but the potential is enormous. The hints from M87 star polarization data suggest that this approach could reveal dark matter properties impossible to access through laboratory experiments. Axion clouds around spinning black holes might produce detectable gravitational waves, providing the first direct evidence for these elusive particles. Astrometric measurements of stars orbiting Sagittarius A star might reveal dark matter spikes through precise gravitational lensing. Each method probes different aspects of dark matter physics, and together they promise to illuminate this invisible component that makes up most of the universe's mass. The search for intermediate mass black holes continues with renewed vigor. These objects, weighing hundreds to hundreds of thousands of solar masses, remain elusive despite hints from gravitational wave detections and observations of certain bright X-ray sources. Future surveys will search for them in dense star clusters, in the centers of dwarf galaxies, and through gravitational wave signals. Confirming their existence and measuring their properties will close a critical gap in our understanding of how black holes form and grow, potentially revealing the seeds from which supermassive black holes arise. Primordial black holes, if they exist, could reshape our understanding of dark matter and the early universe. Recent theoretical work suggests that detecting the explosion of a primordial black hole through Hawking radiation might be far more likely than previously thought, with odds approaching 90% over the next decade, according to some calculations. Such an event would revolutionize physics, providing the first direct observation of Hawking radiation and offering a complete inventory of all particles in nature, including potential dark matter candidates. The coming decade will witness technological marvels that would have seemed like science fiction just years ago. Quantum-enhanced gravitational wave detectors will squeeze light states to reduce quantum noise, pushing sensitivity to theoretical limits. Artificial intelligence algorithms will comb through vast datasets, identifying subtle patterns and anomalies that human analysts might miss. Space-based telescopes operating at wavelengths from radio through gamma rays will coordinate observations, capturing black hole activity across the electromagnetic spectrum simultaneously. Education and public engagement remain crucial to this enterprise. The first image of M87 star captured global imagination, showing that black hole science resonates far beyond academic circles. As observations grow more spectacular and discoveries more frequent, maintaining public interest and support ensures continued funding and inspires the next generation of scientists who will carry this work forward. Every detection, every image, every theoretical breakthrough belongs not just to the researchers involved, but to humanity as a whole, expanding our collective understanding of the cosmos we inhabit. The questions that remain open are profound. How do supermassive black holes form so early in cosmic history? What exactly happens at the singularity? Can information escape from black holes, and if so, how? What role do black holes play in galaxy evolution and star formation across cosmic time? Is there physics beyond general relativity? And can black holes reveal it? These questions drive research agendas, motivate new observations, and inspire theoretical innovations that ripple through all of physics. We stand at a remarkable moment in the history of science. For most of human existence, black holes were purely theoretical constructs, solutions to equations that might not correspond to anything real. Then came indirect evidence through X-ray astronomy and observations of galactic centers. Then gravitational wave detection proved they merge in spectacular collisions. Then direct imaging showed us the shadow of the event horizon itself. Each step brought black holes from abstraction toward tangible reality, from speculation toward established fact. The rapid magnetic field flip at M87 star that opened this journey exemplifies where we are now. We're past the era of simply confirming that black holes exist. We're deep into the era of understanding how they work, studying their detailed behavior, and using them as laboratories for fundamental physics. The flip revealed that our models were incomplete, that the plasma dynamics near event horizons are more complex and dynamic than we realized. Rather than closing questions, each new observation opens new avenues of investigation, challenging us to think more carefully, calculate more precisely, and observe more thoroughly. Looking ahead, the landscape of black hole research stretches toward horizons we can glimpse but not yet reach. LISA will transform gravitational wave astronomy. Next-generation telescopes will image black holes with unprecedented resolution. Theoretical breakthroughs will connect quantum mechanics with general relativity. Dark matter searches will leverage black holes as cosmic particle detectors. All these threads weave together into a grand tapestry depicting the universe's most extreme objects and their central role in cosmic evolution. The universe has given us black holes as gifts, laboratories where the laws of physics manifest in their most extreme forms. Within these objects, space and time exchange roles. Matter compresses to densities found nowhere else. Energy converts to different forms with astonishing efficiency. Quantum mechanics and general relativity meet at boundaries where neither theory alone suffices. Every aspect of fundamental physics finds its ultimate test in black hole environments, and we're finally developing the tools to observe these tests in action. This journey began with surprise, with an observation that defied expectations and demanded explanation. That's how science advances, not through steady accumulation of confirmations, but through anomalies that force rethinking and revision. The magnetic field flip at M87 star isn't just a curiosity, it's a signpost pointing toward deeper understanding, a reminder that nature always harbors surprises for those patient and clever enough to look carefully. We've traveled from the event horizon to the singularity, from stellar mass black holes to supermassive giants, from the mathematics of general relativity to the quantum mysteries of information and entropy. We've seen how black holes shape galaxies, how they merge in cosmic collisions, how they might reveal dark matter, and how they test the very foundations of physics. And we've glimpsed the future, a landscape rich with promise, where new instruments and new ideas will continue pushing the boundaries of knowledge.